now.
Great.
Yes, we are. Okay. Okay, yeah.
So I mute my microphone, yeah?
Yeah. If
Yeah,
everyone mutes and
we can move.
as long as you can see this and all the changes, slide changes. If there's any problem, let me know. Okay, so the title of our presentation today is the 120 cell theory of everything, and this is for TEGS 2024. So the objectives of this presentation, well, we're going to discuss the standard model of particle physics, which is considered the most successful, or one of the most successful scientific models of all times. It contains three gauge groups, SU3 times SU2 plus SU1. And so the goal here is the unification of these groups into a larger group, which also contains gravity. So that would be a theory of everything then. So before that, so the different phases involved, phase one is sort of a grand unified field theory using the 24 cell. Then in stage two, we have 5 copies of those to create a second sort of grand unified field theory model, which is based on the 600 cell. And then finally, we have the 120 cell theory of everything model, which contains 5 copies of the 600 cell. So that's the kind of sketch sort of outline of what we're going to look at. But before we do that, we'll look at previous work. So in terms of grand unified field theories, we have the SU5 gauge field theory, which we looked at in previous talks here. Petit-Salin model, SO10, which contains SU5 as a subgroup, along with the other gauge groups of the standard model. Then there's been some success with it, Tonians, a small marginal sort of success. That's sort of grand unified field theories. But in terms of theories of everything, then we have one that's by Fang and Klee-Irwin, also based on the 600 cell and related to Garrett-Lisi's E8 Lie group model. And then we have other sort of more well-renowned ones, perhaps like string theory and quantum loop gravity. And all of these would share some commonality with the work I'm doing. So we'll start with the 24 cell grand unified field theory, then mapping the standard model particles to the 24 cell. So to begin with, we'll discuss a few things about the 24 cell, its properties, as its name suggests, it has 24 cells, and also 24 vertices, 25 if we include the canonical vertex at the center. These properties make it self-dual in a sense, and which we'll get to later. It's also 3 colorable, which you know, is useful if we're talking about the color charges of SU3. In terms of its construction, we have you could create it with 24 octahedral cells, 1 8 cell and 1 tesseract, or 3 8 cells. And it has isomorphisms with the binary octahedral group, the quaternions, GL23, elements of S8, and the one that we'll be focusing most on, which is the symmetric group of order 4. So originally, the first mapping that I created mapped all of the bosons to the 24 cell in red, and all of the fermions to the dual 24 cell that we see here in yellow. And the purpose of that was because if we take, and this is the self-dual property of the 24 cell, if we take a boson times a boson, we get back a boson. You take a fermion times a fermion, you get back a boson again, and then a boson times a fermion is a fermion. So this quality, self-dual quality of the 24 cell was interesting, and so that was why I chose it as the basis initially. One thing when we put all the particles in, we realize quickly on that there are are 8 vertices that do not get filled. So initially I filled them with the with sort of 8 gravitons, but later I realized that the graviton is most likely at the canonical vertex, which is like equidistant to all of the other vertices, indicating that it interacts with all of them uniformly. So another aspect of the 24 cell is that it has, well, as we mentioned previously, it has 3 8 cells in it. So this is a good candidate for how to place the 3 families of fermions. You could place them on the 3 8 cells. Actually, Garrett Lisi talked about this as well recently, but he was calling the 8 cells cubes, but perhaps he's correcting that in some sort of esoteric way. But regardless, anyway, this research was done a lot earlier, but there's problems with attempting to put all the vertices of the standard, or all the particles of the standard model into the 24 cell. And that is, there's just simply not enough vertices to account for other states like chirality and spin. So in order to do that, we need 4 copies of the fermions. And in order to account for those extra copies, we need to map to the 600 cell. And so that's what we're going to look at today. So we'll be doing that with the symmetric group of called S4. So there's certain prerequisites that we need. So instead of mapping the 3 generations of fermions to the 3 8 cells in the 24 cell, we instead set the 3 families to I, J, K respectively. So that is a sort of conjecture of the model. So also when we place the bosons onto the 24 cell, we can place them on an 8 cell in such a way that they are kind of isomorphic to a cube, and therefore to SU3 gauge group symmetry. But we're not really going to look at that too much. Instead, we'll look at this symmetric S4 map to the 24 cell. So 24 cell and S4 are isomorphic through the S4 conjugacy groups. But if we look at the 24 cell first, we see that the number of cells has this sort of ordered palindromic, I guess, sequence to it, 1 8 6 8 1. Whereas the S4 conjugacy groups, they're close, but they're not exact. So they go 1 6 8 6 3. So it's clear that these 3 transpose groups here need to be moved up, and then some rearrangement has to occur here. So it's so interesting that all of these 4 together create the Klein 4 group. So if we take the coordinates of the 16 cell and think of them as binary numbers, and then sort of invert the binary numbers, excuse me. So this one is the inverse of this one. So then we take the S4 groups and also invert them. Then we can get an isomorphism, which helps us to place S4 on the 16 cell. And then a similar process can be used on the 8 cell. And then that covers all the vertices of the 24 cell, which then allows us to take the S4 conjugacy groups and line them up correctly with the numbers of cells in the 24 cell in that palindromic configuration I mentioned earlier. Finally, once we have all of the fermions then mapped to S4 on the 24 cell, we need to rotate the 24 cells so that the fermions map to the bosons, so we know where to place them. And the way we do that is using Clifford rotations. So there are 12 possible ways to do this rotation using these 2 matrices over here. And yeah, so just sort of the final thing that comes out of all of this then is we have obviously our color charges here based on the 3 colorability of the 24 cell, the unit quaternions, the matrices for GL23, and then the S8 matrices. So as I said before, we map the different families of fermions to IJK. Well, and because we have GL23, this is isomorphic with SL2C or SL23, if you like. But so this group is important in terms of special relativity and the Lorentz group, and GL23 would include the Poincare group. But one thing that's noted about that group is that it's not chiral, so it's difficult to create a chiral theory of symmetry breaking from it. But if we look at the isomorphism, or rather the automorphism with the S8 group, we see that indeed these diagrams are chiral. Some of them go left and some of them go right. And then other ones are more disjoint graphs. So these are directed or digraphs, and these would be the disjoint ones. So if we say that right-handed matter is associated with the right-handed directed graphs, and then left-handed antimatter with the left ones, then we can say that right-handed antimatter, this is right-turning S8 cycle graphs. So we can see that there is no right or left in these graphs, so they're just associated with them as in the same way that these are through the different matrices and elements. So this allows for symmetry breaking because obviously it sorts the right from the left, and then the different matter-antimatter versions from each other. And we say that the W and Z bosons then bind to this group because they too are directed graphs, whereas the photon is not. So that allows for the symmetry breaking. Okay, so we'll move to the 600 cell. In terms of the properties of the 600 cell, it has 120 vertices, 12,000 triangular faces, 720 edges. It's dual to the 120 cell. It's 5 colorable. Its construction can be made out of 5 24 cells, which is why we're interested in it. And it's isomorphic to the icosians, which is a subset of, or a specific set of the Hamiltonian quaternions, binary octaicosahedral group, a coset of E8, the S5 symmetric group, SL25, and spin 4. So to construct the 600 cell using Cartesian coordinates, we can take the 8 vertices of the 8 cell and the 16 from the tesseract. And then when we include those both together, we get the 24 cell, which is isomorphic to S4. The remaining 96 vertices then of 600 cell can be constructed using these coordinates, which or the even permutations of these coordinates, which makes it equivalent to the alternating subgroup A4. So this means that we have 8 copies of A4 that are identical to each other. And then using the composition F of G, where F is equal to A4 and G is a transposition element of S4, such as one of these, we can sort of transpose these groups and create groups of S4. So then we see that we have 4 24 cells for the bosons and 1 24 cell for the, 4 24 cells for the fermions and 1 for the bosons. So this gives us, again, 12 possibilities, showing that this composition, if you like, is isomorphic to rotation. We can see that the bosons all transform into each other, making it an irreducible representation. However, it's harder to say which of the A4 groups grouped together into 24 cells, and which are irreducible representations of each other. And that's really what this graph is attempting to show, that this one maps to this one, and this one to this one. So these are irreducible representations, and so on and so forth with all of the others. Using that method, then we can ostensibly apply all of the particles in terms of chirality, spin up, spin down, matter and antimatter, as well as quarks and leptons and bosons to all the vertices in the 600 cell. The different colors here show which of the particles map to which of the 24 cells. So there's 5 different colors for the 5 different 24 cells that comprise the 600 cell. So these results are only preliminary because there's some work that needs to be done on getting the irreps completely correct. There was a slight sort of misunderstanding or confusion in that, but it's sort of resolved now. So an important aspect, because we have these 5 copies of the 24 cell going into the 600 cell, this makes it equivalent to the exotic inclusion map S4 to S5. So, and an inclusion map simply permutates all the elements around a fixed point. So S5 is an interesting symmetric group. For example, it is the first non-solvable symmetric group. And that means that there's no formula to solve, or it's equivalent to the fact that there's no formula to solve the quintic equation. And this translates into, if we look at other research we've been working on, possibly could be related to the idea that there's no 5-fold crystal symmetries, no hypercharge of 5 for matter particles in the standard model. And it could be related to massive spin to gravity with 5 degrees of freedom, as it goes to massless spin to gravity with 2 degrees of freedom. It's kind of that's something we'll get into later in more detail. And also, it's related to the hexa-Wen and tri-Wen I-Ching leptogenesis particles, which actually make up the 8 missing bosons that we spoke of earlier. But that was subject of another presentation previously. So now we move on to the 120 cell theory of everything. The 120 cell is dual to the 600 cell, I should say. So you can see it has 720 pentagonal faces, 1200 edges, and 600 vertices. Its construction is interesting because it contains all the lower 4D platonic solids, including 5 cells, 8 cells, 16 cells, 24 cell, and snub 24 cells. And it can be constructed using 5 600 cells. The Cartesian coordinates construction are again made up from permutations and even permutations of these coordinates. So we have a 24 cell here, and plus these 96 vertices make a 600 cell, and then there's another 3 600 cells, parts of 600 cells here, and one here as well. So the remaining vertices then make up more 24 cells, which are obviously part of the boson sectors. So again, we can do similar thing that we did before, where we dual rotate the 120 cell this time to see which of the vertices are irreducible representations of each other. And what we find is, again, the 24 cell that we had originally maps to itself, so that's an irreducible representation. And let's say this is another 96 vertices that they map to these versions of themselves. Same here, and we have 2 more. And so that is, and then there'll be another one in here along with the remaining 4 24 cells. So altogether, that's 5 600 cells. And then we can simply map all of these to coordinates. So the interesting or important thing about this is to do with the graviton assignments. So the 120 cell obviously is made from 5 600 cells. Therefore, there are 5 copies of the particles. So the question is, how do you distinguish these different copies from each other? One way is to consider that there are 5 different string theories related to S and T dualities. But perhaps a more useful way of thinking about, or a more obvious way, I guess, would be to consider that the 600 cell itself is made of 5 24 cells, and the 24 cell is comprised of 24 vertices plus, as we mentioned before, 1 canonical vertex at the center, which is a graviton. So therefore, each of the 5 600 cells in the 120 cell has a single canonical graviton particle associated with it, for 5 gravitons in total. So it's sort of 5-dimensional in the sense that massive spin-2 gravitons have 5 degrees of freedom. So you can see here that we have 1, 2, 3, 4, 5 different colors for the 5 600 cells, and each one is mapped to a different graviton, which would be a massive graviton in this case. And this is just sort of a zoomed-in example again of the same thing. So digging deeper into this massive spin-2 graviton aspect, we can first look at massive spin-2 gravity. So we're interested in how to get from a tensor with 16 degrees of freedom to one of 5 degrees, so spin-2. If we look at the other dimensional irreducibles for symmetric group 6, conjugacy group, we see that it goes 16, 9, 5. The irreducible symmetric representations of the tensors is 9-dimensional, and removing the Bianchi identities reduce the number of independent components by 4. So we have 9 minus 4 equals 5. So you see you go from the 16 degrees of freedom in the tensor to 9 and then to 5. So and that's the same as what we have for the symmetric group 6, which is important later on. Then from the massive to the massless spin-2 graviton, which is what we know of and accept generally in the standard model, we take the symmetric tensor with 10 degrees of freedom in 4D, 10 minus the Bianchi identities again gives 6 degrees of freedom, minus the 4 unphysical degrees of freedom of time in the symmetric tensor gives 2 degrees of freedom. So that's how we get to, that's how the spin-2 symmetry of the graviton is created from the tensors. And I'm not an expert on that, but so I've just included a reference to where I got that information from. An important consideration here is this concept of the unbroken 24 cell symmetry. So if we think of the 120 cell, by rotating it, in different directions, let's say 180 degrees, for example, we see that the quark sectors can rotate into the lepton sectors and vice versa. This is obviously not a good property to have, because we can't have quarks transforming into leptons because it would cause the decay of the proton. However, it's worth considering that unlike the 600 cell, the 24 cell is 3-colorable. And as we said before, these 3 different colors that we associate, green, blue, and red, can therefore be associated with a strong force. So this, in a sense, unifies strong force with gravity, because we have the 3 color charges and the 5 gravitons, and they all intermingle and overlap, and with the other forces. So as pointed out earlier, the joule of the 24 cell gives a 600 cell, and the 600 cell is 5 colorable. So once we take the dual of the 5 gravitons, we get a new massless graviton, and also we get a broken lepton and quark color symmetry. And this is because essentially what this means is that 90-degree rotations are forbidden in the 600 cell model. Only 180 degrees are permitted, and therefore the 600 cell has spin-2 symmetry, which is what we expect based on our previous analysis. Moreover, if we look at the symmetric group S6, we see that the 600 cell goes to the 120 cell in the equivalent manner that the exotic inclusion map goes from S5 to S6. So the 120 cell has 600 vertices, obviously, plus the 120 vertices of the 600 cell equals 720 vertices. And we note that the symmetric group S6 has order 720. Sort of a side note here is that the prime factorization of 720 returns again the values for 16, 9, and 5, which were useful in getting from the symmetric tensor down to the mass of gravity. So S6 is the only symmetric group with an outer automorphism. So if we look out, S6 equals C2, which is spin 2. S6 is the resolvent of the quintic equation. This means that S6 could be ostensibly used to resolve the 5-fold gravity and crystal symmetry problems we spoke of earlier. Either way, it is interesting that such a unique group might encapsulate all symmetry groups of the standard model, including the massive and massless gravity forms. So yeah, so it is again, we have the spin 2 that emerges from that. Okay, so applying special relativity in a naive sense to the 120 cell theory of everything. First, we take the core out of the 120 cell. So these are the sort of preliminary matchings of the different leptons, and they're all leptons in this case, with the gravitons and their chirality and spins and antimatter particles included. So once we do that, we can note that if we have the core dodecahedron, we can transform it into a cube here on the left or into a rhombi dodecahedron, and we can do that smoothly. So if we just look from the cube to the rhombi dodecahedron, we can note that the yellow axes here are time, so t, and they have a length of 1 initially. And yes, and they after the transformation they have square root of the length of square root of 3, whereas the white axes x, s are are represented here. They're the space axes, and they disappear completely after transformation. And so that's important from when looking at relativity, because if we're talking about traveling at the speed of light, we want the space to contract and then the time to dilate. So just to run over this again, we have 6 space axes, which reduce to just 3, and 24 time axes. So if you're to count all the yellow lines, there's 24 of those, but they will also reduce to 3 because they're equivalent to the other groups. That's when it's a cube, though. It changes as it rotates. Or sorry, yeah, as it transforms. But if we look at this transformation, we can see that the 3 time axes, if you like, on the corner appear to be rotating and scaling. So that's kind of interesting. We also note that space contracts from a length of 2 to 0 at c, whereas, as we mentioned earlier, time dilates from 1 to square root of 3, or this value. However, if it starts off in a dodecahedron, which it would when we remove the core or when we just take any of the dodecahedral cells of the 120 cell, then it is going to, the rotation will be 150 divided by 2. The reason why it's such a large number is because we'll be dealing with hyperbolic space shortly, and that gives 37.5 degrees. Therefore, in this model, 37.5 degrees equals 45 degrees, so the 37.5 degrees of the hyperbolic space, four-dimensional
Just one clarification, if
yes.
you don't mind.
No.
It should be 140 divided by 4, right?
Sorry, what?
That number of dodecahedron rotation is 150 by 2, but it should be 150 by 4, right? 37, because 150 by 2 is 75.
Oh yeah. Well, yeah. There's some weirdness going there with the mathematics, because we're dealing with hyperbolic space. So I'll get into that later. Okay. So here we have 37.5 degrees in hyperbolic space, which is equal to 45 degrees in Minkowski space. Well, that's four-dimensional hyperbolic space as well, I should say. So this is again the core of the 120 cell just removed, and I'm showing how it transforms from the dodecahedron into the rhombi dodecahedron. And we note that some of the vertices, which are representative of these particles, as the lengths contract, so as the object is speeding up in space in terms of how whether it gets close to the speed of light or not, the lengths contract in the different dimensions, and so the particles, which are fermions in this case, must wind up at the same location and therefore in the same state, which means that they, because of the Pauli exclusion principle, would mean that they have to turn into bosons to do that, presumably. Okay, so now we'll look at the hyperbolic 24 or 120 cell, which is about adding general relativity to the model. So we begin with the fundamental domain, which is a pyritohedron cube, and all of the images in the next section pretty much are all from a video called Not a Knot, I think, which is available on YouTube and was created by Gunn et al. In 1991. So to begin with, yeah, we take our fundamental domain, as I showed earlier, and we're going to follow this process. So first step will be to switch on the red axes, which will tile the fundamental domain in the x-axis, and then we'll switch on the green axes and the blue, and finally the blue axes. So after switching on the green axes, we'll get we'll tile a plane in the xy plane, I guess, and then after we switch on the blue axes, we tile all of space infinitely. Then, in order to convert this pyritohedral cube from, like normal Euclidean space into hyperbolic space, we need to take four copies. So if you imagine you have the 4 cubes around the edges, but then we increase the degrees so that we transform the cube like into a dodecahedron like we saw before, while making sure that there's still 4 dodecahedrons around each of these axes. And that creates hyperbolic space. So when we remove the edges, or well, we'll look at that in a minute, but you can see we could add the particles from the 120 cell standard model to each of these vertices. And so again, this is just saying the same thing. We transform the cubes into dodecahedrons, preserve the angles so that 4 dodecahedron form around a single axis, which you can see quite well here. And then this creates 4D hyperbolic space, which is an analog to 4D Minkowski space, and therefore has the potential to include general relativity. If we get rid of the gray faces on this, we can kind of see more how this structure tiles infinitely out in all dimensions. And again, we have the particle of the core dodecahedron from the 120 cell. The particle representations are mapped to this structure, but it would continue out and then be tiled infinitely. Is the concept. So if we look to understand the next bit, we're going to have to look at some more of the basics of hyperbolic geometry, which is also called Lobachevskian geometry. We look at this example down here, for instance, we see that in Lobachevskian space, light rays curve around. So you could see yourself, for example, back again. And this is related to the concept of fundamental domains here. So that this car is the same as this, and this tree is the same as this tree, so on and so forth. And so the red dot at the center here is referred to as the link complement. And so using this, we can stretch our fundamental domain, if you like, into a cone, which is pretty much the same geometry. And at the limit, this becomes a cylinder. So if this stretches to infinity, that's what we get. So we can do a similar thing with our four-dimensional hyperbolic 120 cell. Essentially, the different colored axes now are the link complements, and as we increase the angle, or sorry, decrease the angles around these links, we see that the link complements get shorter, which is equivalent to space getting contracted, whereas our other axes, which are time axes, get longer. And then at the limit, we see that space is contracted completely and time is now infinite. So this would be sort of a model then for quantum, like, you know, black holes on a quantum level, if you like. And these are just those again, but side by side. I suppose another way then to apply general relativity here is to say that if you're orbiting around a star, which is in a sense represented by one of the fundamental domains, or rather one of the link complements, if you travel around once a year, but if we decrease the angle here, so that we have 7, it means it will take you 1.75 years to complete an orbit in this gravitational field, whereas, you know, if it goes to infinity, then it will obviously take you an infinite amount of time to do one orbit, which would be around like a black hole, although it's hard to say what distance you're orbiting around the singularity. So essentially, we've taken the cube or the dodecahedron and then transformed it into another rhombi dodecahedron, but this time in four-dimensional hyperbolic space. So that's kind of what this is attempting to show. You can see the various vertices there of the rhombi dodecahedron. And it's also interesting to point out that rotating not in the XY plane, but in the Z plane, let's say, the rhombi dodecahedron also has spin 2, which is, you know, so that keeps coming back, which is important if this is a system of gravity and it's supposed to include gravity. And more importantly, I suppose when we include gravity in the standard model, we're going to wind up with quantum gravity essentially. So the 24 or the dodecahedron cells of the 120 cell standard model mapping quantized space-time. That's what we're saying. And the map of the quantum 120 cell to hyperbolic space quantizes gravity, as we've seen in terms of general relativity. So gravitational time dilation is a function of circumambulation around axes, like those orbits I said, whereas special relativistic time dilation is a function of the lengths of the edges, and that's also true here. For more on hyperbolic spaces, you can see these references. So in conclusion, the 24 cell covers the three generations: electroweak coupling, SG3 color charge, matter-antimatter positioning, and boson-fermion sectors using the symmetric group 4. And the 600 cell covers spin, statistics, and chirality using the exotic inclusion map from S4 to S5. The 120 cell introduces canonical gravitons with 5 degrees of freedom. These reduce to the massless spin 2 graviton in the 600 cell dual representation. 120 cell has 600 vertices plus the 120 vertices of the 600 cell equals 720 vertices, which is isomorphic to the symmetric group S6. S6 is the only symmetric group with an outer order morphism, which makes it equivalent to C2 or S spin 2. And the symmetric group 6 resolves the quintic, therefore the massive 5-dimensional bosons. Transforming the 120 cell into hyperbolic tiling unifies quantum mechanics with special relativity and general relativity. And that is the claim. And the standard model plus the graviton, quantum gravity, can be contained within S6 or SL29 as a whole. And in SL25, SL211, the Gaussians, SO4, spin 4 is a double cover, and S symmetric group 5 in parts. So I guess that's really it. If there was one take home that I want you to have, is that the dodecahedron cells of the 120 cell hyperbolic 4-dimensional model quantize spacetime. And those are the references you can see. And that's it. Thank you very much. Okay.
Well, what I can say,
yes,
Christopher, you turned from the last presentation, you turned the knob all the way up. It was a wonderful mathematical physics presentation and research. I think you are getting very close to maybe next year to present your PhD, to be ready. I don't know. I get the feeling that you are now an expert in Koch group theory, obviously, in order to get in such a level of. And I think your model is beautiful. It's beautiful.
Thanks very much.
It's not just beautiful, but it's clean-cut research. It's very nice presented. It's not ambiguous something. It's you can understand it very well. As much I can. You are much more expert than me now in Koch group theory. So yes. I'm very impressed. And this you must really go to the research guide profile of Antonios Valamontes, because he also gets to the same conclusion that essentially space-time, the structure, the connections of all the gravitons are forming dodecahedrons. So
yes.
imagine that the space-time now is a matrix, and you have inside the matrix these springs. But now imagine that the associations of the springs are forming the vertices are forming dodecahedrons, and the center points of the dodecahedrons are the gravitons, something like that.
Right.
So I think you are really spot on. It's a very, very nice, very interesting piece of mathematical physics research. Definitely, you have shown that you can unify your model helps to make new associations of the Koch group theory, and actually beautiful presented with animations and geometrically, and you can really extract from your model. That's the benefit of this model. You can extract new associations and new correlations which were
Yes.
not obvious before. I think that is the most contribution, the very important contribution of your research.
That's
it's difficult, of course. I couldn't even. I imagined I grasped only maybe 10% of all the research.
Okay.
You did a tremendous work from the last time. You turned you turned the knob from up to the maximum now.
Yes.
Presentation-wise, it was perfect. So again, congrats, man. Congrats. Really, I'm very proud. I'm very proud to have learned you, and I think you must publish it. I mean, in a normal index journal, you need to do this to get out. It's very interesting mathematical physics research. It's a theory of everything.
Great, thank you. Yeah, I'd love to publish it as well. There's a few little things that need to be sorted out before I do that, but it's getting there. It's close to being.
Yeah. I think by the next year. How long are you now in the PhD? 2 years?
3. I'm just 3, maybe 3.5, coming up to 3.5. But
okay. I think next year you will be ready. I think next year you will be ready to.
Yes.
To have the Viva.
Yeah.
So I have a few questions.
Oh, great. Yeah.
I like very much that you model considers the transition of a massive graviton to a massless graviton.
Yeah.
I was very impressed about this because the problem with the massive gravity, with a massive graviton, is the range. The range, because both light and gravity have infinite range. But if you have something massive, then you cannot have the infinite range. So there's a contradiction there.
Yeah.
So for example, the Z boson and the W plus and minus boson, these are massive particles, massive bosons. Because they are massive, that's why they have only limited range to the weak interactions. The weak interactions are very limited range. It's less than minus 15 power of 10 meters. The reason why the range of action is so small is exactly because they are massive. So a massive graviton, in my opinion, is wrong. You cannot have a massive graviton because we observe that gravity is infinite, like light, like electromagnetism.
Yeah,
that's the problem.
Absolutely.
But you explain it very wonderful that you can transform the massive graviton to mathematically with your theory, with your model, the vector model, the group coach model. You can transform it by just changing the degrees of freedom. You can make it being massless. So you say that you go in slide 28. I want you, if you can elaborate more on this in slide 28. Can you go to slide 28?
Yeah, that's it there, I think.
So how I want me if you can explain me what you mean exactly about decrease of freedom, because you described that you go from a massive graviton of 2 degrees of freedom to a massless for 5 degrees of freedom. So what exactly are this degree of freedom? I mean, are they spatial dimensions X, Y, Z and time? And what's going on there?
Yeah, no, it's a good question. It's kind of, it's the other way around. So we have for a massive graviton with 5 degrees of freedom, and then the massless one is the 2 degrees of freedom, right? Because it's a massless spin 2 particle.
So which one is more fundamental, the massless or the massive? Which is the most fundamental?
Well, actually, technically the massive one is more fundamental. Mm-hmm. Because so if we have an unbroken 120 cell symmetry, so the higher energy one is the 120 cell, okay, and then when we take the joule of that, we get the 600 cell, and that's where the symmetry breaking happens in terms of the lepton and quark color symmetries, and that also gives us back our because when we include the 600 cell, then in the 120 cell, we go from 600 vertices to 720, which gives us this S6 symmetric group. which again has spin 2. So it's another way of approaching it. And also the prime factorization, which I think, Rajan, you'd probably be interested in. Yeah, and we did work on that previously, didn't we? So basically we get these different degrees of freedom popping out again, which is a 16. So this would be like the, your metric tensor or your stress energy tensor.
Okay, I understand.
Yeah, and those have different degrees of freedom. 16 degrees of freedom to begin with. And then there's different ways of reducing these, which I got from Stack Exchange. But so this part of the research, as I mentioned, is a little bit outside of my sort of area of expertise, I guess. But it does relate back to what we talked about in previous slides with the irreducible representations. But here they're applying it in terms of the tensors. So I'm not entirely sure of the details of that. It's a bit hard to discover, but we do see the same.
We have to look into Bianchi identities.
That's how you say it, is it? I was calling it Bianchi or something.
Bianchi. What?
Yeah, something like that.
Bianchi. Okay. So you have to use that. Sure. Yeah. I think that's there.
So yes. if I understand correctly, do you want to add something more, or I don't want to interrupt you?
No, yeah, I was just going to repeat the basic method of how they get from 16 to 5, but then so that kind of relates back to the S6 symmetric group, which is important because it has all of the like 720 vertices in it, which relates back to the automorphic outer automorphism spin 2 group. So
you start with a massive 5 degrees of freedom graviton, yes. And then somehow, as you describe, the 2 degrees of freedom of massless graviton pops out.
Yes.
So you end up, the end product is the massless. That's what we see. Okay.
So essentially, we would take the where is it? Like if we were to take a dodecahedral cell here, and then if you take the average of all of those points in that cell, we will get a point at the center, which should be the dual. So, and you do that for all the cells, you should get the dual representation of the 120 cell. Although see, there's a thing about the 24 cell being self-dual, and it doesn't mean that there's like a dual polytope that sits inside so there are 24 vertices in the 24 cell, and there's also 24 cells, but it's not dual in the sense that each of those vertices lies at the center of those cells. Some of them are actually sitting on the faces, so it's a bit strange that in that way. So it could be the same thing here, that some of the vertices are sitting on faces and some of them are not. I haven't proved that yet, and I haven't found out which is correct. It would seem logical to assume that they are at the center of the cells, though.
So your model, Christopher, is isotropic and uniform and homogeneous. I mean, if it's not disturbed, if space-time is not disturbed, you don't have particles of the standard model, then the space-time is the structure is the dodecahedron structure is everywhere we see the same. Is it isotropic and homogeneous?
Yeah.
You assume that space is not disturbed. You don't have particles in it, just free space.
Well, I suppose the model for free space would be more along this structure here, because this is hyperbolic and it's 4-dimensional. So this is obviously just the beginning of there'll be later parts of the research which examine other aspects of this in more detail, like why we only see 3 dimensions of space, for example, and so that's going to, so there is an analogy there between, I think, is it the Wick rotations? So you have
Wick rotations, yeah.
Yeah, so you're taking the metric, the space-time metric, into into a four-dimensional Euclidean
Mm-hmm.
metric. So obviously, I haven't prepared that here. That's going to take a bit more work, but essentially we can do a similar thing where we will rotate the 120 cell hyperbolic 120 cell into. So basically, what we'll do is we'll transform this back into this kind of structure.
I see.
Yeah, and then these will be 24. Each of these will be a tesseract, and then we can rotate this four-dimensional tesseract in such a way that it will basically just look like a grid system. Is what I'm saying, like a three-dimensional grid system.
It's more like a chaotic isotropic grid system. It's symmetry out of chaos. It's very beautiful. I like it very much because you get all these different rotations, but it's they are homogeneous everywhere. So you could say that the free space is homogeneous according to your model.
Right. Yeah, but there is so because this structure here is made out of a fundamental domain, everything gets just copied over, you know?
Yeah.
But
we don't see all these dimensions. Maybe that's also important. But maybe the dark sector is not homogeneous. But if it's projected in our space time, the four-dimensional space time, including time, then we see that like homogeneous. But maybe in the dark sector, it's not that so much. I mean the cell structure, because I don't know. The dodecahedron itself, is it a symmetric cell? Can you describe it like a symmetric cell, a homogeneous cell? I mean, it's not totally symmetric, right?
No, it is a regular dodecahedron inside the. Sorry, I just have to get to it. So like this is very symmetric. Like these objects are the most symmetric objects in the universe, kind of, that are known. I think that's what they're called. You know, they're related to these exceptional Lie groups. There's something exceptional about them. So, yeah, I mean, there's a distortion going on here because of how it's projected into 3 dimensions from 4D. But in 4D, yeah, this is very regular. The 600 cell is also really regular, and same with the 24 cell. So, but when we get to these grids, so if we transform one of those dodecahedrons into a cube, and that's going to be 4-dimensional, there's a way of transforming that 4-dimensional cube into this, in a sense, like this grid pattern, and that then will look three-dimensional, but only from a specific angle. So if we were to move, like, we can rotate around it in any direction in 3D space and it will still look like a grid system. But in order for that to happen, it means that it has to be rotating in a gauge transformation in the 4th dimension so that it appears always the same. Do you know?
Wow.
Yeah, because otherwise it'll break apart.
It's very smart. It's I mean, God is a very smart guy anyway.
Yes.
But you are also very smart that we know there's do we really discover things or invent things?
Well, this is it. I mean,
I think we always discover things that they are already there.
Yes, exactly. I'm merely relating the information here.
Yes. I mean,
invention is inside of discovery. Discovery is the larger sphere, you know.
Well, yeah, when you have to go out of our way to discover the things, I guess, in the first place, and well, obviously this work was done by Gunn and different people. I've forgotten who. There's Thurston. Thurston is another person who came up with all of this. A lot of the maths involved in this, though, is not actually that relevant to what would be going on here, because this is, like I say, a fundamental domain. You have all of these copies, but the 120 cell will extend much further than any one of the fundamental domains pictured here. So then that would have to be tiled infinitely.
I think I will share with you the ResearchGate profile of Antonios Valamontes, because this guy is also very, now I think he's watching right now. I told him if he wants to participate, but he has a problem. He had an accident, a very bad accident. He broke his shoulder.
Okay.
And it cannot. It's very difficult for him to type in and so on. But usually, I think you will benefit in looking also his model, because he's talking about the dodecahedron. That he describes the fabric of space-time having a dodecahedron, a grid symmetric structure.
Yeah.
So I will show you his research profile, and you'll really look up his research.
I have done. I've looked into it. Yeah.
He's also talking about he has more than, I don't know, maybe more than 50 articles.
Yeah, he's talking
about the dodecahedron, the
structure
of the universe. I think and it's not a coincidence that you also resulted to the dodecahedron. There must be some truth behind this.
Yeah, this is it. As soon as I saw his work, I knew you were kind of working with him.
You know him? Yeah, okay.
Well, no, I saw through you. You were working. I think you're
working
with him. Yeah,
we wrote a paper together. Yeah.
So when I saw that, I was like, when I saw a dodecahedron, I was like, aha, right. So I have to, I have to look at this to see.
Yeah, but my model. My model is chaotic, so the gravitons don't have any special orientation in free space. That's why, and I have a reason for that. Maybe I'm wrong, but it doesn't matter anyway. I like to explain why I insist that the orientation is chaotic. There's no specific symmetry. If I'm talking now for free space, not if it's disturbed and you have excitations of the quantum fields, you have particles, just free space, undisturbed free space. Leave it alone, don't push it, something, so it's calm, it's at rest. So you have space-time at rest. Imagine some intergalactic region where there's nothing going on. There's no planets, there are no Mars, just only quantum form, and that's it. So when I did my ferrocell, my ferrolens research, I came across a very interesting phenomenon, magnetic phenomenon. It's called superparamagnetism. Superparamagnetism. So what is this thing? You have very fine grinded iron fillings. So it's not iron fillings. It's actually iron rust. So it's iron 3, oxygen 4.
Okay.
Is it
it's actually some kind of the oxide of iron oxide.
Is it magnetite?
It's magnetite. Yes, exactly. Magnetite. It's three atoms of irons bonded with 4 atoms of oxygen.
Great.
So you have a very fine grain. So you have these small spheres that are about an average 10 nanometers in diameter. 10 nanometers.
Wow.
Minus 9. Brilliant. So all these have a magnetic moment. They have a vector.
Right.
But when it's inside the thin film, which is imagine you have billion of these small spheres, and you dilute them in a carbon solution.
Yes.
Like benzene, for example. And that gives you the fluidic film. The fluidic film, which makes the ferrolens. Yeah. So you diffuse. You put this fine grain powder, which has grains of 10 nanometers. You dilute it maybe 0.2% of hydrocarbon solution,
Yeah.
which is normally benzene, could be some other hydrocarbon solution, and these guys are inside swimming.
Yeah.
So, but the Brownian motion, the thermodynamic vibration they have because the temperature overcomes the magnetic moment. The magnetic moments never orient; they're just randomly oriented. So
Okay.
you get here a sphere of 10 nanometers which has North Pole here. The
Yeah.
other sphere is here, and they're all randomly because
Yes.
they have thermal vibrations, and the magnetic moment is not strong enough to overcome the thermonic vibration. You understand?
Okay.
So that's why these guys are always randomly orienting the magnetic moments.
Okay.
But this effect, what this effect makes, because magnetism means coherence in the orientation. If you have all the magnetic moments oriented in the same direction, then you have magnetism.
Yes.
If they are randomly, they cancel each other out.
Right.
So the magnetic film is not magnetic.
Yes.
If at rest, it's not magnetic. It has no magnetism.
Right.
But if you now bring an external magnetic use and a magnet, a bar magnet, if you bring it close, then all these guys orient the suns to the same direction of the external magnetic field, and then the magnetic field becomes magnetic.
Of course.
Yeah.
Yes.
So super paramagnetism is exactly this phenomenon. At rest, you have no magnetism, but under the external influence of an external field, it becomes very magnetized. But all the small spheres, 10 nanometer spheres, they all get aligned with the external magnetic field, and now the solution becomes very magnetic, very close to ferromagnetic. Ferromagnetic.
Of course.
Which is different because if in the case of paramagnetism, you have only very slight magnetic effect. The material gets very slightly magnetized, like aluminum. Aluminum is paramagnetic.
Okay. Yes.
Yeah, it can be magnetized, but under very strong external field.
Right.
But the material itself it's not magnetic very much. But super paramagnetic materials, which how you make a super paramagnetic material, you take a material, an iron material and a ferromagnetic material, and you grind it to very small powder. If you make it very small powder, then you get super paramagnetic effect. That's the trick. So even iron, if you grind it to very small powder structures, spheres, 10 nanometers and so on, and then it becomes super paramagnetic and has exactly this effect. Alone, it doesn't magnetize, and when you apply an external field, it gets very magnetic.
Right.
And as soon you you cancel the external magnetic field, it immediately loses its magnetism.
Oh, okay, very interesting.
Yeah.
It's a very good.
That's why. So why I'm talking now about this? Because my model of the gravitons is essentially a ring, and all these rings are chaotic inside the free space. But if you start to disturb free space, then they become aligned and create magnetic flux lines, and then you have magnetic flux, and you have solitons. You have formations of these magnetic lines. Imagine each magnetic line is like a hose, a water hose, and you have cylinders, and when they all align, they make one structure.
Yeah.
So you have rings. If you put it together, then you make a hose, a water hose. A tube. So the flux is tubes of gravitons which come together, and by magically form now a manifold. And this manifold can be an electron, can be a quark, whatever. That's so my model. I'm not saying it could be totally wrong. Free space, if it's not the undisturbed space, is chaotic. The gravitons inside have no specific orientation. It's like a soup, like a condensate. It's like, for example, has water a grid? In water, there's no grid of atoms. They're chaotic. It's fluid. So my model of space-time is like a fluid. So it has no grid. It has no definite structure. But that's my.
Yes.
I'm very impressed with your research now.
Yeah.
It's beautiful presented. All the math, the presentations, the animations. It's very nice. Again, Christopher, congratulations.
Great. Thanks very much, Manuel. Yeah, because so like maybe following on from sort of Rajan's sort of bearing that you take, like, yeah, I don't feel that my model, though the one that I presented today, necessarily needs to be in conflict with what you're suggesting. There could be a way that both of them exist. There's sort of what I'm presenting it's very ordered, but there must be some slight abstraction to it, I would say, because like all the particles are arranged in vertices, and it's nicely ordered, but the universe is not like that. There's a lot of chaos. So I think
no, but space-time could be very nicely ordered. Free space, doesn't really need to be. Could be very nice ordered. Free space.
Right. Yeah. So I kind of think of it more as almost as like an abstraction that allows for the gauge symmetries to occur.
Yeah. I mean, the beauty of your research is not. My research is no more about ontology. You have to go to the real low level, but. You describe something different. You take it's actually a beyond the standard model theory. Your theory, it's a beyond the standard. So you try to extend. You don't say something revolutionary, something totally discarding the whole model. You get the model, you describe it, you find new associations, new correlations, and then you unite it with gravity, and you show that it's possible. It's an effective model. You cannot say, nobody can say that understands exactly nature. You don't. I mean, now physics tends maybe in the late 80s or 90s. I'm sorry, in the 18th century, 19th century, maybe then physicists try to describe ontologically the things. But now the theories are more effective theories.
Yeah,
you don't try to. You don't know. You cannot know exactly what is going on, but you describe a model which agrees with predictions. So you beautifully united the Gauge models, the SU2 and SU3 and all that stuff, and you extended it to include anti-gravity.
Yes,
very nice work.
Thank you very much. Yeah, the general relativity side of things. Yes, because I mean, I was thinking about your research then as well, because you have these flux tubes, and they, I think you had them lining up so they create the lines of force within the, the toroidal. Lines of force.
I mean. I imagine my models are woven like a thread with these flux tubes. So you have the flux line, which is actually gravitons. Each graviton is a ring. Imagine a ring, a torus. And then you connect all this. Then you have a flux tube. You have a flux line, which is in the center. It's made out from gravitons. All the flux, what is the flux? The flux is distortions of space-time. Everything is distortion of space. Gravity is distortion of space-time. Electromagnetism is also distortion of space-time. It's a different distortion. So if you macroscopically distort space, then you have gravity. If you try just to make with your finger manifolds inside the soup, the space-time soup, then you have electromagnetism. You have the particle and so on. So imagine now that each line I distort is a flux line, which are gravitons glued together, forming a hose like a water hose, like a tube. So each flux line, now it's the flux line. The flux tube is the fundamental thread by which all particles of the standard model are woven. All the manifolds of this. So my theory describes the flux manifold of each particle, and doesn't matter if it's massive or massless. But one thing that my research concludes is if you want to have a massive particle, then the manifold of the flux lines must have three spatial dimensions, x, y, z. It must have volume. If you have a massless particle like a photon, then essentially it's 2D.
Right.
has only two spatial dimensions. Spatial, no time, just x, y.
Yeah, yeah.
So, but
Similar to John's
yeah, I
work.
mean,
And of
the
course,
z, yeah, but of
that's
course, the z dimension, it doesn't mean that it has no thickness.
oh,
The thickness is one Planck length.
okay, yeah, yeah, that
So
makes
it's
sense.
essentially it's a two, yeah, something like that, yeah.
Yeah, yeah. So that's a lot of. I mean, yeah, even in the standard model, what they would include like a third dimension for mass and stuff like.
Yeah, massless particles cannot occupy a volume in space.
That's
In my
yes.
theory, massless particles cannot occupy. Only massive particle. I mean, it's I correlate the two things: mass with volume, the same. For me, if you want to have mass, you must have occupy a volume in space.
Yeah.
If the particle is massive, it must essentially its manifold must be energy manifold must be must have three dimensions, x, y, z. Must have volume.
Well,
Without,
yes.
yeah.
Do you remember the idea that I shared with you on? I think I sent you an email on it, and it was about this idea of so you have the tube that you're talking about with all of the gravitons and their
aligned gravitons. Yeah.
Right, but then you imagine, right, if you zoom into one of those rings, that ring is also comprised of little rings. So it's another tube made of rings, and then you can just keep zooming in and zooming in on each of the.
Oh, you mean concentric rings? Yeah.
Not concentric, no, like exactly like you're talking about, where there's your graviton ring, and then there's another one here next to it, and it creates a tube.
Yeah.
But then if you zoom in on one of those gravitons,
okay, yeah, of course, yeah. But yeah, you have to put a cutoff in your theory, unless you get mad. If you can go in and in and in. Yeah,
that's what I'm saying. Why not go on forever?
Why you cannot go on forever? Yeah, of course, yeah.
Why not?
Because then you have to go to do mathematics with infinities, and physics don't like it. But mathematical physics, if you do mathematical physics, no problem.
Yes.
Doing mathematical physics.
Yeah,
Go all the way in.
Yeah, it would just be a fun thing, because you could ask, like, what is the fractal dimension then of this graviton particle?
Yeah, it has no bottom. You can go up to infinity.
Yeah.
Can, of course, yeah.
I don't know how you go about, I guess, calculating that.
It's a problem, yeah. So you essentially, if you want to do mathematical physics, you can go to infinity. But if you want to do physics and mathematics, you have to put a cutoff.
Yeah, but if you say like so each of those gravitons would have some energy, like it doesn't have mass, but it has some energy, and then, but is if that single graviton is composed of all of these other little gravitons, then it is like, and that single graviton has a specific energy value, then that specific energy value is the sum of all of these infinite ones, and one's getting smaller and smaller, which would mean that it's getting more and more energetic.
Yes, of course.
So you have some sort of
you have ultraviolet divergence. Yeah, you end up again with ultraviolet divergence.
Right.
You get again to infinity. So you end up again with the same problem, because the stopped in the Planck length. Because you cannot go lower the Planck length, then there's no meaning. Then you have to exceed. If you want to go below the Planck length, you essentially exceed the speed limit of the light, which is not permitted in special relativity. So by axiom, they say no, you cannot have something smaller than the Planck length, right? That's the whole thing. That's why they put the cutoff in the standard model of particles. They put the cutoff in the Planck length, because if you see the mass, if you want to go smaller than the Planck length, you have essentially must go to superluminal. You have to exceed the speed of light, which is unacceptable.
So, but the difference between the difference between real space and imaginary space. So if it is a real space, it has to be minimum Planck length. If it is less than Planck length, then become imaginary space.
Yeah.
So,
but I mean, I believe the reality, our reality, the substrate of our reality is sub-Planck. It's not Planck.
Yes.
Oh, okay.
I mean,
Of course,
because
yes.
then energy is not. If you just put a hard stop in the Planck length, then you have a problem again. Another problem. The energy is not preserved.
Oh,
No, that's
You
why
get a free energy. Then you get free energy.
Emmanuel,
Free
what
energy,
I'm
which
looking
is
at, yeah,
that's a problem.
Emmanuel and Christopher, I'm looking into the conservation of energy. Actually, conservation of energy is true. In my new paper, I talk
Yeah.
about time conservation. So
Okay.
the
With timer conservation.
yeah.
I read something. Yeah, I read something.
Yeah. So the energy we talk about not necessarily it's a quantum energy that is conserved, not the total. See, for example, noise, right? Noise energy is not conserved. If it's energy is noise, that's not conserved. So so conservation is a very restricted way, So when you talk about quantum energy, I talk that the time conservation. So if the time is conserved, that's why we have all this ability to
That's very interesting, Rajan. Very interesting. Yeah.
Yeah, it is an
I like
interesting
that,
idea.
So you have time conservation, but you don't have
the
spatial
total
and
energy
motion
conservation.
Yeah.
So to say,
very
entropy is not
interesting,
conserved. Yeah, if it's become entropic,
Well, is the
it's
speed
not
of light
conserved.
still conserved? I mean, you could throw out
Yeah.
the speed of light as a constant and have the conservation of time and space time.
So you have to contract space in order to preserve time. You have to contract space. So it's special relativity.
Oh, would you call that a conservation of time? Yeah, because I'm thinking more along the lines that you're conserving the speed of light. I suppose, yeah, but that's all interrelated then.
Yeah, it's all.
Yeah.
I mean, Einstein said that speed is the ultimate. Yeah, the speed of light is the absolute reference. That's what special relativity says. And in order to make the speed of light absolute, space-time must contract.
The time dilates, doesn't it?
Yeah, the space and time dilates, but the speed of light is always fixed.
Well, the time has to dilate and the space has to contract.
Exactly.
Yeah. So that was another thing that if you look at the model that I showed with the 120 cell, you'll notice that all of the vertices, all of the axes, whether it's X, Y, or Z, they all contract.
Yes, I saw that. Yeah, the animation, beautiful. Yeah.
Yes, by the same amount. So that's interesting because ordinarily when we consider, and you know a good bit about this because sort of still grasping a lot of it. But so in special relativity, you have an object that let's say it's traveling close to the speed of light hypothetically, and it's supposed to length contract in the direction of travel, but and not on the other.
Always in the direction of travel. Yeah.
Yeah. So, but
vector. Yeah.
What I'm showing in this model is that it would contract in all directions.
Okay. Okay.
Yes.
Makes sense. Makes sense. Yeah. I mean, the mass of the object is contracting in the direction of travel. Doesn't mean that space-time has to do the same thing. Space-time can't be deformed from this object traveling inside it.
Yes.
In any degrees of freedom. Yeah. Yeah.
I would say that would have to be the case. So
yes, I mean,
there's some great ideas like of I don't know what example they use, but they have like a rocket going through a barn or something, and you shut both doors.
I mean, if you imagine a mattress and you press with your finger goes one way, one dimension.
Yeah.
Maybe even contracts also because the pressure. But the mattress is the grid inside the mattress. All the springs are making all the kinds of contractions and expansions, right?
Yeah.
So the space-time itself is not contracting only in the one direction. It can contract and expand simultaneously in every XYZ direction.
Yeah, I suppose, especially if you
makes sense. I mean, if you accept that space-time is a medium and it has some kind of elasticity, then it makes sense.
Yeah, you probably need an extra dimension to account for those expansions and perhaps, but which is
Yeah.
fine in this model because you've got that implicitly.
Yeah, no, I think there's no problem with your model. Your model is consistent.
Yeah,
with
I agree with
special relativity. Yeah, no problem.
yeah, I fully agree with Emmanuel. It's a very comprehensive model, Christopher.
Oh,
So
thanks
I think
very much.
yeah, it does require a lot of more, like Emmanuel said, people should look seriously because I think it's going to solve a lot of the problems.
Great.
You know,
Yeah.
and also visual. See, I believe in visual geometry is very, very important because that's part of the proof, part of the evidence. You know, it's not the final proof, but that's the first step in proving. You know, you are seeing what you are seeing. You are seeing the sky. You are seeing all the stars. It's very similar. You know, so you are associating the two together, the physical aspects, and very, very important. Of course, the abstract aspects, I agree. So one of the things I can tell you, you talked about 24 dimensions, right? I think it's 127. And you said the time axis reduces to 2, but that's where the model, I think we can talk about later also. Eventually, I'm getting the particle. See, I have published 3 of them, and they are very important. Almost they accepted. The 4th one will be particle. At that time, your model will come. I mean, yours and Emmanuel's thing come. And I think Emmanuel also, we talk about graviton. We are going to do some work together. But the idea is that the 24, if I have 6, the rank 6 tensor, 6 times 4, that's your 4 hyperdimensional space. So it does match that. I mean, we can talk about later. But when I went through, it, it does make sense. But if you can pull up that, it's much earlier.
I'll just hide that.
Probably like a 20 or something, 20th or much earlier. When you talk about 120 cell.
Oh, it's around here. This one, I think.
Yeah, exactly. So you said 24 time axis, right? So in that one.
Yeah. There's a lot of work to be done on this, Rajan, I think, actually. Because even as I was talking, I was like, oh, actually, you know, because as I was talking, I noticed, like, so we have these 6 space axes. So they're the white ones, yeah? So you can see that there's going to be 6 for each face of the cube. But obviously, you know, two of each are mirror images, so they're the same direction. So we really just go down to 3, and then we can do the same with because this line here is going to be separate to this one because it breaks when you're moving faster, and that's how we go from like the order 4 crystal symmetries into this weird order 5 crystal symmetry that we were talking about. Remember, we were saying it's hidden in there somewhere. And that's how so that's an interesting thing that we're going to have to look into more. But so this is an interesting point though, because if we play this a bit.
Yes.
I really like this one.
The previous slide. I want to. Sure. Yes. There where we have the equal one. No, there was a formula.
Oh.
Yes. Yeah, the previous one.
This one.
No, previous. Yeah, that was equations. So you say here 150 divided by 2. Yeah. So you better use not this notation, the equal. Just use the equivalency notation.
Yeah.
You know the 3 lines.
Oh,
the 3 parallel lines. Yeah. Because this mathematically is not very. You know, it's problem. So you just use the 3 parallel lines. 3. You know, you have 3 parallel lines.
Oh, okay.
The equality. Yeah. So it's more.
You can also use. You can use the equal sign. Then you put a what you call the greater than equal sign, right? And 4 dots, and then equal to that. That means you are transferring to that. I mean, it's not equation. It's not an algebraic. I mean.
Yeah. That's why Rajan asks you. You know, for the presentation, because
Yeah.
it sounds weird. It's not equal. It's I mean it's
I know
some
what you
kind of
mean, yeah.
proportionality. Yeah. So you should actually don't use just a friendly advice. Nothing.
No, that's great.
Yeah.
Those are good tips, especially if I'm not like that used to working in hyperbolic space. So I can't even really recall. Like I would have to sit down and recall how I'm getting this exact results. It's to do with like if we look at the three lines here on the corner, they rotate by an amount which is 90 degrees, I think. And if we're dealing with hyperbolic geometry at some point later on, that's going to be more than 90 degrees. I think it might turn out to be 150 or something like that. So then we have to divide by 2 because we only want to get halfway between.
Very nicely animations. Which
yeah,
program
I like this one.
Very nice.
This is a wonderful thing.
Yeah, this is great. This is from I got it off Wikipedia. You can find it on there. And Tom Rouen did that one.
Nice. Yeah.
And then so
my friend Wolfgang Daimler died.
From sorry to hear that. Yeah,
very sad. It was my friend. He was my friend, and he did all of these animations. I used this wonderful animation.
Yeah.
This guy is 77-year-olds. After many years battle with cancer, yeah, he had made more than 10 surgeries of.
All right.
Wolfgang, right? Wolfgang. Yeah, Wolfgang.
Yes. Wolfgang Daimler. He has actually a ResearchGate profile.
All right, I'll check it out. Be interesting to see more of his animations. They were good. All right, so
he also visited me 2 years ago. He visited me here in Crete. He came from Germany and he visited me for a week or so.
Wow.
Like Rajan. Yeah.
Oh, yeah. Thanks. Yeah.
Oh, nice.
I think you were in Germany, right? You did a little bit work.
Yes, I lived.
No, I
lived 7 years during my school.
7 years.
My basic fundamental foundation. I was
in Germany.
German, yeah. But I was at the age of 14. I came back to Greece, so I spent there from 7 years old to 14.
Wow.
Yeah, 14. Just seven
Where
years
in Germany? Which what is the name of the city? Germany? What place?
Oh, Ludwigshafen.
Oh,
yeah, Ludwig, like Beethoven, Ludwig Beethoven.
Oh, Ludwig.
Hafen is the port. It's the port, for the ships. So it's Ludwigshafen. Yeah, German uses many synthetic works. So
is it near Munich?
Like waterfall, waterfall.
Sorry? Is it near Munich or?
Yeah, it's close. It's close to Munich. Yeah.
Maybe the Austrian border or something like that.
No, not Munich. More like Frankfurt and Köln. Frankfurt. Frankfurt.
Oh, okay. Very nice.
Frankfurt Wurst. The Wiener. Frankfurt Wiener. Hot dog.
Oh yes. Especially the Frankfurters.
Yeah.
Oh yeah.
Frankfurt sausages. Yeah, there was this.
Oh yeah. So with this so you can see there, Rajan, you've got the three the three axes there, and obviously because it's a cube, you've got 8 of them, so that's 24. Yeah. But these again will be, this one is equivalent to that one, and that one's equivalent to this one, so it all reduces to 3. But while it's rotating, it's interesting, like how much does that symmetry break? I don't know, but one thing to consider that I actually forgot to mention in the presentation is that all of these rotations that occur in the transformation that you see in the animation, they all rotate in the same direction, regardless of whether they're on this side or the other side of the cube, which is a strange fact. Yeah, and that could we could then relate that to electroweak symmetry breaking again, you know, that there's like a specific direction of rotation that's important in the model. And also it could indicate that, like, when we're talking about something like what you mentioned earlier, Emmanuel, about like pressing your finger into a mattress or something, that there's a curvature in space-time. So it could suggest that that curvature in like a higher dimension is always in one direction, you know? It's because this transformation,
like gravity, like macroscopic classical gravity, yeah.
Right, because this transformation is describing gravity or faster than, or traveling very fast. So if you were traveling very fast, like when you warp the space as you move, that warping is always in a specific direction. And maybe if it was, see, the odd thing is you could say, well, maybe if it happened, if the warping happened in the opposite direction, you'd get anti-gravity or something. But I'm not sure if you would, because you can actually do this transformation between the cubes and the dodecahedron.
I mean, anti-gravity is the dark energy, the expansion of the universe. You could say that anti-gravity is
right. Yeah, well,
dark energy, the expanding of the universe.
Right. Well, so but it is not true that doing it in the opposite. Sorry. So if we were to rotate in the other direction, we would just wind up at the same object anyway, in a sense. So it doesn't really. It wouldn't create anti-gravity because space would still contract, time would still expand. So yeah. So I don't think it would be.
Actually, all this expansion of the universe, I watch it like a baby growing. You know, a molecule is growing up; it's getting bigger, bigger, bigger. Or you have a small pretzel, you put it in the oven, and it starts to inflating, to expand. I think it's a natural process. Everything grows and gets bigger.
Yes, maybe.
Usually, everything grows and gets bigger, and then it bursts. And,
oh yeah, that's a big bang, right?
Yeah, then you have
but it's not
bang.
Big bang.
Then you have the Penrose cyclic Big Bang universe. You get a bang, and then you get back to a singularity, and then it grows back, and then again bang, and all that stuff.
Things grow, and then they have a limit, you know, like any person, we grow, we get to a size, and then we start to shrink again. I think that's probably
interesting thing we find. You know, when I did material science, we talk about volume free energy and surface free energy. You know, so the growth occurs because there is a lot of surface energy, so it distributes to volume free energy, so it keeps expanding. But at some point, the volume free energy becomes greater than surface free energy. You see that? So it contracts again. Of course, what happens is, like in pendulum, what happens is the surface, it keeps growing, but the volume free energy becomes greater because of the momentum. You know, it keeps going, but it realizes the surface energy is decreasing a lot. That differential will pull it back inside.
Oh, interesting.
Okay. Yeah. So it's a very simple model. I was trying to, you know, you can actually, it's a very simple equation you can do.
I believe that nature uses the same tricks over and over, the same tricks.
Yes.
I think that nature does this. It doesn't invent new. It has a set of tricks, and then it recreates. It uses the same tricks in any scale, macroscopic, small. Yeah.
Like you said, yeah.
I have actually argued with other people that I don't like this quantum physics and classical physics. I don't like this distinction. I think there's no such distinction. Physics is just one. It's only physics we understand and physics we don't understand. That's the distinction. We have physics we understand and physics we don't understand. There's no quantum physics and classical physics and that's I don't like this.
No, only from the point of view of conservation for energy, I think the quantum physics is useful. You know, like what Planck said, because of ultraviolet catastrophe, he introduced the idea of Planck units, right? So to remove, because you do experiment, you cannot get infinite temperature. Doesn't make any sense. You don't get it. So how do you resolve the ultraviolet catastrophe? So he came up with the idea that the energy packets are there, so you cannot extend. So that's the only good thing. That's the only thing. But other than that, there is no difference, like you said, Emmanuel. Yeah.
So I
That's
see these comments here are Fugazi News. This is all to do with the dodecahedral model as it relates to the 120 cell model. Because I recall this about from your colleagues' work there, the work you've done with them, that about 72 degrees of rotation, 180 degrees, and 120 degrees around the different symmetry axes. Can you see that, Manuel? The comment on screen.
Yeah.
Yes. No. No. I don't see anything now.
Oh.
If you go into the
yes. You can see me.
Yes. Oh yes, I see you. Yes. But I don't see any
at the
slides.
Bottom of the screen down there.
At the bottom.
Okay. Oh, yes. Yes, of course. Yes.
You recognize this is
yes. Right. Yeah. Okay. So is that a video, YouTube video?
No, this is because you asked people to. This is people who are watching who are commenting on the.
Okay. Right. All right. Well, that's the comments. Yeah. Okay.
You asked someone. I can read it out there. The 72-degree rotation around one of the 5-fold symmetry axes, 120-degree rotation around one of the 3-fold symmetry axes, and then 180-degree rotation around one of the 2-fold symmetry axes. This is interesting, and those would be the different axes within the dodecahedron, I guess. See, there's a problem though, because we would be dealing with a 4-dimensional version, but then moreover, the hyperbolic aspect means that you can go from 72 degrees of rotation up to infinity degrees as you approach like a black hole or something. So,
but you don't see all these degrees of freedom. Maybe you don't see this macroscopically. Maybe some of them are hidden. Hidden variables, and you don't see them. Maybe that's the problem.
No, but I think the idea though is that it should happen like on the lower scale. Like that's kind of the whole point. Like we get down to the gauge groups and say, well, this is the structure of the gauge groups when unified, and then when we expand it out into the hyperbolic sphere and all of that. So where we can even leave out the hyperbolic part and just show how the length contractions work with the space and time. So that it insinuates then that some of the edges linking the particles together are not just space, but they are time. Some of them are time elements. Some of them are purely space. So it's quite strange. It's like a network of sort of quantized space-time on a lower level.
You can imagine it. You can imagine also this similar to measurement problem we have with quantum mechanics. The measurement problem is that we observe time the measurement only specific binary states, and we cannot observe the immediate states. So we call it superposition. So it's in superposition. That's a different word to say that we don't have a clue what's going on there. But we see only spin up and spin down. And in the electron, we see only 2 binary states, spin up and spin down. Doesn't mean that it's quantum. What are the intermediate states? It can be, imagine that you have the magnetic vector of the electron, can go this way, can take any sort of angles, like quantum computing. But in physics, when we can measure only spin up and spin down. So then we say we have quantum mechanics. Doesn't mean actually that it's not classical. It could take it could take all the intermediate states and then go down, spin down. But quantum mechanics says no, it doesn't make this rotation. It just magically transforms from here to here.
Okay.
That's quantum mechanics. What I think is
it's the measurement problem. Yeah. So you have hidden variables. Sorry, Rajan. You have hidden variables you cannot see. Of course, then comes the Bell inequality theorem and says no, it's not classical. You definitely it doesn't. The vector. Imagine a sphere, the electron sphere. It flips. but in order to flip, you have to rotate.
Yeah, yeah.
Even if you don't do this, you rotate. You have intermediate states.
Yeah.
So this is classical physics. So these are, you can say, hidden variables. But quantum mechanics says no, you don't have this. You magically, I don't know how you get from here. That's quantum mechanics. So you don't see the intermediate states. Intermediate states means classical physics. But quantum mechanics, quantum physics has no intermediate states.
That's interesting.
It's either up or down.
Yeah,
that's a problem. It's a measurement problem. And now comes this guy. I sent you his research. I found his name. He has a video on YouTube and actually in a paper in Zenodo, which proves that actually the Bell inequality wrong.
Oh, I watched that video. Yeah, you sent that on to me.
With local hidden variables, he proves with local hidden variables, you can have local hidden variables, which means classical mechanics.
Yeah.
You have and still it still doesn't violate the Bell inequality.
Very good.
Brilliant research. Even I will ask him if he can present us here in this.
Oh wow, yeah, that would be great.
Yeah, I will ask him if he can present his work.
Well, he's very
brilliant. The name. Let me please find his name and
sure.
The research, because I think this is a brilliant research, and of course this guy has also problem in publishing his work. The same problem, whatever you got this journal editors were very, very frustrating. Doesn't do things.
I mean, just
so
thinking about this.
You have the paper
earlier about. I mean, well, that would be okay actually in this model because.
But one possibility is that what happens is a real scalar state. Scalar is the one that you can measure, but the other states are tensor states, which means you cannot measure that. So in the final level of the quantum, it may be that way. We can go to brain. The brain is two-dimensional. It doesn't have volume. So it's massless, right?
Okay.
The brain state. BRANE, brain. So, and then the M theory talks about that. So I'm in the next one, the next episode, I will cover that, whatever people are saying. But then I'm applying that aspect also. I put them together. I say M-brain theory. Like you mentioned about the 5 different string theories.
Yes.
I mean, instead of that, you said you can explain it the other way, 120 cell.
Well, I'm thinking actually you could, because you get like 5 copies of the 600 cell in the 120 cell, and each of those has a massive graviton associated with it. So then you have you could say, well, maybe these are related to these 5 copies of string theory with this S and T duality, but that's quite complicated mathematics, and also the way in which these different dualities are associated. They're not all interconnected like these 600 cells are. They're very one is connected to the other, which is connected to the other, and then back again. That kind of way. So it's not like a full, but that might be because the mathematics they're dealing with at that point gets quite complicated. I think they're moving into areas of modular forms and elliptic curves and stuff. And even Witten was like, okay, well, this is interesting, but we have a connection now. But perhaps you could go deeper and find more and more connections. But I don't know. That's very intense work. So I'm leaving that there as a possibility. So I want to allow for a link to string theory as well as the direction that I chose to go in, which I think is simpler and also allows for a larger inclusion of gauge groups. The fact that everything is really unified under the symmetric group S6 and it's outer automorphism.
The Lie group, right? The Lie group.
Well, it's a symmetric group. It's also connected to there's a Lie group connected to the 600 cell, I believe, which would be kind of like the Acacions. And then there obviously must be one then for the 120 cell as well. I'm just not sure what it is. But you can take both of them together then and say, well, unify everything and say, unify both the the non-broken and the broken symmetries into one larger group, which is kind of strange. Yeah, so that was kind of.
It's a dodecahedron to icosahedron. I mean, you can construct from icosahedron.
So guys, I found this. The name of the author of this paper is Samuel Hidman. I don't know if I pronounce it correct.
Right.
Samuel Hidman. I think he's American, and he has the paper is the first. Actually the links.
Hedeman.
Yeah.
Samuel Hedeman. Hedeman.
Yeah, Samuel Hedeman. Yeah.
I think that's right. And the paper's on zenodo.org. Yeah,
yes,
there's the YouTube link. I've actually, I watched that. It's very good. It's like 50 minutes long. 50 minutes long.
Yeah, something like that. Yeah. It's worth watching.
Yeah, I did watch it. It's very, it's quite involved though. At the time, I wasn't really able to grok it, and fully understand it. So, but I think now I might have a better concept. But
the definitive proof of quantum mechanics is the Bell inequality theorem and the experiments, which got also the Nobel Prize to last
Alan Specht.
Yeah, the Alan, the French guy, and the other one. But if this is broken now, that's very interesting. If the inequality is broken, I mean, this could be a changer. Yeah, I was actually excited. I had actually chatted with this guy. We had exchanged some emails, and he was also pleased that I consider his work very important. Yeah. But the funny thing is, he proves that the inequality holds with local variables. So it's not because you can use because one of the subsequences of the Well inequality is you have no local variables. So you have communication not with the speed of light. So the propagator of information cannot be the speed of light, because if you put the Alice and Bob, the two, the receiver and transmitter, if you put it in a superluminal distance, which means a distance that cannot explain communication via light, it's too much. The time it takes is too much to explain the instantaneous action we actually observe in an experiment of a quantum entanglement experiment.
Right.
So if you, this always a consequence of the quantum mechanics and the Bell inequality is also non-locality. You have some kind of action, but which cannot explain with speed of light. So it's like if something is interacting with each other, but it's not using electromagnetism, nor gravity.
It's gravity.
Continuous interaction. So, but this guy proves it with local variables, local hidden variables, and he explained it he explained his model very nicely to me with a paradigm, with an example. So, the quantum entanglement is generated at birth when the two particles are created.
Yeah.
Which essentially means that they will have a different spin. Imagine two cylinders, and they are created, and the one turns clockwise, and the other turns anti-clockwise, and then they're getting apart. That's actually the process of generating a quantum entangled pair. You put the photons through special crystals, and this creates two opposite spinning photons that are flying away. That's exactly the part of. So now the theorist says even if the particles are getting 2 galaxies away, they are tangled. Whatever, when you measure the state in the Alice location, immediately it will determine the state of the other particle. It's like if they are connected via spook action of the distance. So he says, no, there's nothing spooky action at a distance. Imagine these two cylinders, one spins like that, the other spins like that at the genesis. And then they went away, very far away. quantum the quantum entanglement experiment, many people don't understand this, demands that at the time Alice makes the measurement, at the same exact time Bob will also do the measurement. And when the measurement is done, entanglement is destroyed. It's only once. The pair is not when you do a measurement, you destroy also the entanglement. So the entanglement is only one for the one measurement. So because angular momentum is preserved, it's exactly if you do the measurement this time, how you can explain that? So imagine you have a cylinder, yeah, and you make a dot with a marker, and this dot now spins with a rate. But you have the tangle pair which spins in the other direction, but at the same time the dots are in proportional equivalent positions around the circle. So when you do one say 10 seconds after they got separated, 10 seconds and 15 microseconds, both do the measurement, the dots will be correlated. So the correlation is at the genesis. It has nothing to do with communication.
Oh, okay. Yeah, I see. Yeah.
You get the
It's like a resonance. It's like a resonance.
They're synchronized. Resonance. Yeah.
Resonance coupling. Resonance coupling.
You get the circle.
Yeah,
you have the dot.
And
this spins. Yeah, and the other spins. But quantum entanglement specifically demands that Bob and Alice do the measurement at the same moment.
Okay, but that was the always the idea, you know, that if you have two pairs of socks and I send one pair of socks, I send one to one hand side of the universe, and then you check.
Well,
look,
yeah, exactly. But
socks. So therefore,
but the difference is
the right hand socks. So then. But that's that was always the argument. So it's like
but this guy,
so you can't just restate it. There has to be some proper mathematical reason why this is the case.
But why this guy now? Why Samuel proves now that this is the case? Because he proves it with formal. Because he uses for the electron the classical model, like me. He also adds the intermediate state. So he says, no, it's not getting magically the spin up to spin down. It rotates actually. So now his system is classical. But that's exactly the meaning of hidden variables. Hidden variables mean, especially if they are local, means classical physics. So when he uses now, he doesn't use the quantum model. He makes the model classical. He says, no, the electron has this spin now, and it doesn't magically go from here to here. It rotates, so it uses now the intermediate states, the so-called superposition. And when he does this, then he can prove with mathematics. You saw the video that no, you can have a quantum entanglement with local hidden variables, which means with classical physics, Newtonian physics.
Well, yeah, I mean, I watched the video, but like I said, it was. I couldn't understand it, so I have to go back and look. But
it's very complicated. Yeah, you have to read.
It's not said in a. It would be nice if it was said in a way at the end. Oh, and here's a bit of a, because at the time I was trying to get my head around. I think it was last week or maybe the week before we were talking about quantum entanglements and hidden states, and then I was like, oh, okay, I get it now. But I think even my conception at the time might have been completely polar opposite to the way it actually is.
It's a very difficult subject to grasp.
Closed off because of entropy rather than, as I was saying, because of lack of entropy. And then you're bringing in another concept altogether, which is this, this kind of rotation. But I mean, it's very related. I can see how it'd be related. But see, the way you're explaining things, Emmanuel, it's very easy to understand you. You explain it in a very clear way. But up until this point where it's then it becomes a little bit sort of cloudy. It's well, why, just because something can rotate, does that, well, I suppose it's not.
Yeah, what's the problem? Yeah, why they don't like the rotation thing? Yeah.
I think it's just an issue at sort of at the core of of the scientific debate that's being had for the last maybe 70 years or more, that they really haven't described it very well, what it actually is that they're talking about, you know, and Bell, I suppose Bell's things.
I mean, the core of quantum mechanics, really the core, is the Bell inequality, because you get the statistics. You get, if you do the experiment, the statistics are not classical statistics; they are pure probabilistic statistics.
Yes,
that's the problem. Our measurements are not giving us the whole picture, so we result to probabilistic statistics.
But they've adopted that, and like they're saying, they like this kind of thing, you know. So
yeah, it's simple, but it's actually a problem. We cannot measure these things. It's very difficult. I tell you what the problem is. I tell you now what exactly the problem is. When you measure an electron, in order to measure its spin, you have to bring an external field.
Yes.
Okay? You have to apply an external field. So you cannot control the spin of the electron. Imagine your external field is pointing up. So you have north and south. Now imagine the electron like a small sphere. When you apply the field in order to measure the spin, you can end up with the electron having spin either spin up or spin down. You cannot control this.
Yes.
That's the problem. If you could control this, then you have classical. So one of the points that you cannot use quantum entanglement to transfer any information is because you cannot control what to send.
Right. Okay.
So because say you want to send bit 1, okay, you apply your field pointing up.
Okay.
But it's not guaranteed that the spin of the electron will point up and align with external field. It can point up either parallel, which means parallel means they have the same direction, anti-parallel.
I'm just not entirely sure why a classical rotation would solve the issue, but maybe
yes,
Edmund can explain it to us. But
it's an axiom. It's an axiom. It's quantum mechanics. You are not allowed to have intermediate states. You either have spin up. It's like an axiom in mathematics.
Okay. So if this axiom is broken, then that's the end.
Because we cannot measure, Christopher. We cannot measure these states. It's not possible. So we cannot measure it. If we cannot measure it, we don't have physics. Maybe you can have mathematics, but you don't have. If you don't have in mathematics, if you cannot experimentally observe it, it doesn't exist. Like that. It's imagination. So because we cannot measure it, you cannot make it like that. You can have the electron like that or that, and you cannot control it. So you cannot send the information you want. You cannot say now I send bit 1, and now I send bit 0. Electron has a mind of its own. Like that, so you cannot control the information you send.
Fair enough.
You cannot use communication. That's the problem. So that's called the measurement problem. Measurement problems, actually, we have an incomplete picture of reality. That's a measurement problem.
So,
that's mechanics,
So, Emmanuel and Christopher, so recently I'm going to publishing something, it's almost there, signal and noise. You know, fundamentally, I derive abstract things. So what happens is, what you're describing is, what is signal? What is noise, right?
Yeah.
So in terms of the signal is a specific type of noise, when they are in coherence and they have resonance. So the signal produces only that. I mean, there are more things, but I'm trying to give one picture of it.
Yeah.
So when it is up, you get the signal. When it's down, you get signal. But all other places, you get noise. That's why you cannot measure it.
Superposition.
So the signal to noise ratio is too low. You cannot measure it. It doesn't mean it's not there. It may be there, but you cannot measure it. Whereas when it's up and it's aligned, you can measure it. when it's down. But you do, like you Emmanuel said, you don't know whether it's up or down. The electron decides either way.
It's
It
random.
can be up or down. Yeah, you cannot control it. That's true. That's a measurement problem. But before that, the idea is that the signal is because the signal is up and down. Otherwise, other states are noise. The signal to noise ratio is too low. So that's why in one of the earlier papers on configuring observables, I mentioned about critical signal to noise ratio, which means that you have to, if it's below critical signal to noise ratio, you cannot measure it. So it has to be above that.
Okay, so
I think that is the concept that's going to help, because then that will explain everything, classical and quantum.
There's an interesting guy who talks about you know, Einstein's work on the photoelectric effect, and so you throw all these charged particles like electrons at a plate, and some of the photons bounce off. So
only for blue light. Only for blue light, you get.
It's not to do with the intensity of the light, but the frequency can change the number of particles or the frequency of the light coming off. But
do you know why? Do you know why, Christopher? Do you know why the frequency?
The point I'm trying to make here is that the particles come in, and it's to do. You know, there's a quanta that needs to be exceeded before the photons.
Yeah, but do you know why? Do you know why?
Wait a second. So but the issue is that he's saying that could be that it's a threshold limit. So it's like when the energy it's like a capacitor. So the energy has to get up, and then it will expel the photon, which is interesting. So he's kind of coming at it again from a classical point of view, using thresholds, which is kind of more in line with your thinking, I think, or Emmanuel.
About this the photoelectric effect. Why the frequency? Because when you get high frequency, the wavelength is small. So imagine you have some kind of smoke rings. So light is like a smoke ring, you know, a vortex ring. And then you have the atoms. You have the atoms in the material, in the metal. When the smoke ring is too big, which means large wavelength or low frequency, translates. Imagine now a large wavelength. You have a smoke ring with a very long perimeter, very long. So so this is, for example, the atom, and now you get this very big ring coming the photon. If it's very big, it just will pass. It will not interact. When you have short wavelength, which means higher frequency, now the size of the photon becomes comparable with the atom. Now the two will interact.
No, I don't mean. Is it not to do with amplitude though? Like
it's not amplitude. The wavelength is the frequency. The higher the frequency, the smaller the wavelength.
So imagine how then what do they? When they talk about the intensity of the light, that would be what? Not
just imagine like the momentum. Intensity is like the momentum. So
the amount of energy in the light,
speed, and then they collide, something like that. Yeah.
Right. So the amount of energy, I guess, or yeah. Okay. So it wouldn't be the amplitude, because that's an interesting thing. Like if you have the light coming from a distant star, let's say, and and they say that the universe is expanding so that the light gets stretched, but it doesn't. Shouldn't it get stretched in all directions? You know, including its amplitude. Wouldn't the amplitude increase? But they never. Yeah.
Each frequency can have its own amplitude. It can be a low amplitude or high amplitude. Each frequency has independent amplitude. Low frequency. So each frequency will have its own amplitude. So
the amplitude doesn't correspond to energy then, like it would in sound.
Well, it's like the weighted average of the whole thing. Like one frequency may have small amplitude, another frequency high amplitude. So that frequency will show up a lot more intensity in terms of intensity. So intensity is summation of the amplitude and the frequency. You know,
there's like a relationship between the frequency and the amplitude.
So,
Why would there be a relationship?
No, not related. Each frequency, suppose it has what, let's say a frequency of 10 power 18 has amplitude of like 10 or something. Okay. The frequency of 10 to the power 12 may have amplitude of 100. So that's become visual range almost. So it will show up more. That amplitude will show up more because the amplitude is essentially the intensity. It will show the intensity of that frequency.
Oh, okay. Well, that's
like blue color, even blue color and red color. If the blue color has more amplitude, it has more intensity. So the blue color will show up.
I think the problem is that the problem with Christopher is he's confusing photons with light. Of course, when you have light, amplitude, you have more area. The amplitude, of course, contributes to the power, to the energy. But in the case, the formula, the energy H, the Planck constant times F, refers to photons, not to light. Yeah. So of course, amplitude, the larger the amplitude, the more energy you. But this is for light, not for photons. Energy equals the Planck equation. Energy is the Planck constant times the frequency, refers to photons, not to light, to discrete photons. And because photons don't have mass,
yeah, that makes sense.
Yeah,
but don't you think that the photon? So you're saying that there's no relationship between frequency and photon?
So imagine the whole thing with light, all that stuff. Imagine that you are inside water up to the knees in the sea, and you receive periodically waves. So the period, the wavelength is the length from one wave to the other. That's the wavelength.
Right.
And at the time, the inverse, the reciprocal of the time is the frequency, yeah? But the amplitude is the height. It's something like the height.
Yes,
the height of the waves.
Exactly.
But if it's just photons, because photons don't have mass, you cannot have amplitude. They're massless.
Oh, yeah.
Something like that. But again, it's very complicated because light has momentum.
Amplitude, then.
Yeah, but light has momentum. It's very complicated.
Although you can think of the frequency of a the energy of a massless particle is the energy, which is tied to its frequency and its wavelength.
Yeah,
not its amplitude. No, so that makes sense. So, but it's almost like a kind of circular thing then a little bit. So, because they talk about the frequency, so the intensity must be different then from
intensity
either, So that's just how much. Anyway, it's a bit odd.
One way,
one
way to think of is light is like a composite of photons.
Yeah,
it's a composite of photons.
Okay,
but photons are individual.
There's a couple of questions here with what is the practical significance, I guess, of the theory they're asking? I would say that
somebody's asking.
Yes. I can put it on the screen.
So, who is that? Somebody watching our thing?
Yes, Geo Intuition is the name. So, what is the practical significance?
It could be your person. I mean,
of the research. Yeah, the practical. Yeah, that's good.
Yes, of course, it's related to the presentation and the research.
Samuel.
Okay. So I suppose the big thing about a theory of everything and grand unified field theories, but specifically theories of everything, is the idea that we attempt to unify all the four fundamental forces into one gauge group, and that is a thing that people have been looking to do for a very long time. And I mean, they call it this grand title theory of everything, but even when you discover this, it's not going to help you, like, say, figure out like what every car is doing on the planet or everything that's going on inside the body of a dog or something. It's just not. It's not an actual theory of everything, but it's restricted to what it's restricted to. But if we can also unify quantum mechanics and these of the standard model in this scenario with general relativity. That's another big kind of request, I suppose. People are saying, well, what is the unification? And so that's what I think it brings as well. And by doing that, then we get a theory of quantum gravity. That's one of the other claims, because we're down at the level of where the particles are interacting with their gauge groups. And we also see the length contraction and time dilation of in general relativity, which is gravity, the bending of space-time. And so we see that we have a nascent theory of quantum gravity, which could be expanded upon later, excuse me. And so I think ultimately, like with the later research, we're looking at expanding knowledge into sort of higher dimensions and different non-Euclidean dimensions to almost give us a better understanding of our place in the universe on a large scale, and that. So it's kind of, I think the benefits from this, or well, I don't know if you call them practical, but I think they're more on a philosophical level of understanding how the universe works. And
I again, when I ask this question, whoever one asks this question, my question is simple. Say, for example, the next big thing now, which is going on with the technology, which is fusion. Yeah, nuclear fusion to make clean energy without the problems of the different process, the
fission or fusion is
fusion, the nuclear, the explosion, which is very radioactive. So my answer is very simple. We have to understand what's going on in order to succeed in this technological marvel, the new thing, the nuclear fusion, which will potentially solve the problem, the energy problem of the planet. We have to understand what's going on in nature. For example, if we want to go to a different solar system, we have to reach speeds very close, a good fraction of the speed of light. But this is not possible if with chemical propulsion. It's impossible. So we have to find different ways. But in order to find different ways, we have to master nature. We have to understand what's going on. The first people which mastered the fire, you have to master something. You have to master nature in order to make you technological marvels. So that's my answer. So it's
very good.
It's not just philosophical. I disagree with you in that.
Well, no, I'm just saying. So they asked me like, what is the practical significance of my model? I'm just saying that I don't have a practical significance of it at the moment, because
at the moment, because with models like yours, we can unify theory. But when you have unified theory, then we can master also gravity. We can master, and when we can master gravity, then we have UFOs. Yeah, if we master gravity, we have UFOs. So that's the answer.
Yes. So I'm just not clear on how to get from where we are, or from where that. Let's say the model is totally correct. How do we go from there to the next step? But
the problem is people don't understand gravity. It's a force of nature. You cannot shield gravity. Gravity penetrates everything. So if you cannot shield gravity, you cannot have also anti-gravity.
Well, yeah, I mean, this is it. Maybe, perhaps the anti-gravity, because I spoke of the fact that the rotation happens only in one direction, and that there might be a possibility of doing it in the opposite direction. And I was also saying, well, all the symmetries sort of look the same when you do that, but that might be incorrect. Like it might actually be so that the other direction leads to anti-gravity, but I don't think it does. And so it's just a guess. There might be something along those lines that we could look at. Okay, so the next question is, so this is an interesting question. Could you show the connection of these constructions to, example, chemical elements or to different crystal structure forms? Yeah, that is a good question, because that was briefly touched upon in one of the slides where I spoke about fivefold crystal structures. and its relationship to, well, actually the I Ching. And that's a different episode or a different live stream we did on leptogenesis. The interesting thing about that, so there's 8 leptogenesis particles in the 24-cell model. And those particles, so that when the universe starts off, you just have those, you have 6 of those particles, and then they interact to create a further 2, and then all of those eradicate to to create the particles that we know of in the standard model. So that's the concept there. And they have there's a link there to a hypercharge of 5. There's no particles with a hypercharge of 5 in the standard model, at least in the matter section. So this is the idea. So there's a relationship then between 5-fold symmetries, the I Ching, and these hypercharge, lack of a hypercharge of 5. So and in that system there has to be, well, there doesn't have to be, but I'm suggesting maybe to solve some problems you'd need mass and, or because in Einstein's theory you can have solutions for like basically negative mass. So with that, within there maybe there could be some, with a negative mass possibly you could have negative anti-gravity. I'm thinking, so that might be where anti-gravity is hiding in the model, because there's no dark matter particles in this model. That's something that came up, unless I'm wrong about the leptogenesis particles and somehow there's dark matter particles in there. But I think I solved the dark matter problem in a different way, where I say there's 3 different types of space. So there's conventional space, and that's all to do with the Marangoni catastrophe that I looked into. So it's a separate thing. But actually, because there could be these 3 different types of space, that seems to comport again with the 3 different generations of matter. So perhaps they are linked energetically together with these 3 different kinds of space.
It's like a phase transition. Phase transition of space-time. Yeah.
Right. So it's interesting because there's a big problem at the moment between MOND and then dark matter, because MOND seems to predict things well, but dark matter predicts other parts.
I don't like MOND. Sorry.
Fair enough.
I don't like
MOND. So I don't use either models. I don't believe in either. But so you could have 2 clusters as moving together, and then they move through each other, but they leave some of, as they go away, they leave some of the
the bullet.
Yeah. So then this goes against MOND's explanation, because it shouldn't leave a residue. But if it's a different kind of space that has a cohesion to it, a different type of slightly different value for the gravitational constant, if you like, then that would cause this binding. So it's a fun idea. Then as for the 3rd type of space, that doesn't actually exist in our universe yet, and if it ever does arrive, it will destroy the universe. But it will eventually arrive, is the prediction. So, but when it will destroy it, it will completely reorder the universe. I think there's a good chance the Earth will survive. So,
hopefully. So, guys, it was very nice. I think we have to go now.
Okay, thanks a million.
I really enjoyed your presentation.
Thank you, Emmanuel. Yeah.
And also to you, Rajan. Also, thank you very much.
Thank you.
Really enjoyed
Yeah.
it, guys.
Yeah.
So I lately have a hobby now. I play 3D games. So
really?
I actually play now Witcher 3, which is one of the best. Really strongly recommend Witcher 3. It's an older game, but they did a remake of I think 2022 of the game. Yeah, I got a good graphics card, NVIDIA card.
Is that based on a film or something? Or
sorry?
Is it a video? Is it based on a movie?
It's an RPG. Yeah, Witcher. I think they did actually a Netflix series.
Oh, okay.
Witcher 3. Yeah, but it's not that good. It's not that Witcher. The game it's much better.
So this is VR, like with a headset and all that?
No, I don't like VR. Just normal, with a game controller. Yeah.
Oh, like on a TV?
No, in my computer, in my PC.
Oh, okay, right, yes.
Yeah, yeah.
Okay, well, thanks a million
No,
for
I don't know.
it's very it was interesting, and you gave a lot of very good, as you tend to do, explanations on difficult concepts in physics. I find them
hopefully
difficult.
we could help you, Rajan.
Thank you. Yeah, no, it was useful.
You.
But thank you again for the presentation. It was actually brilliant. Thank you,
Great.
guys. Bye bye.
Thank you. Yeah, we'll talk later. Yeah.
And
we'll see you next
in the
week.
meantime, we'll attempt to continue with these answering some of these questions.
Yeah.
Well, so there was a question about chemical elements. We're not really going to go into that because we're kind of like at a slightly lower level, but yeah, I mean, there could be something later on to do with that. But so are these consistent with the laws of crystallography? I suppose we kind of went into that again with the five-fold crystal symmetry. Although I guess to get a real proper understanding of that, you'd want to watch the lepto.
Also, you mentioned about IJK.
Yes.
So that is connected with crystallography. There is a
right.
Yeah, because we use IJK. I mean, those indices of the for describe the crystallography directions. So I don't know whether you can find a connection.
Yeah, to that. I suppose. Yeah, it's pity Emmanuel already left because I was.
Yeah, I was about to tell him that. Yeah.
We didn't get it. He could have answered his own question. What's the gravitons model? How connected to? Oh yeah. So how is the model connected to the reality? That I don't know. I mean, it's operating on a very small scale, like even beneath.
I think we are going to. I'm going to work with Emmanuel some of it because he finds some correlation to what we did before. So that then could bring the reality because my theory is a little abstract, but now it's coming towards the real aspects, and then we connect with the Christopher's thing, and also after that Emmanuel's thing. I think all three could
is
be
about Emmanuel's graviton model. How does it connect to reality?
Yeah.
I don't know the answer to that. I suppose you'll have to ask Emmanuel when he gets back, possibly. And does the concept have a prediction? Again, I assume this is for Emmanuel, so I cannot answer that. I'm not sure which
one they're referring to.
Yeah, because mine's pretty complicated. I assume it's talking about mine, and it goes to the basic laws of nature. I don't know. I find nature pretty complicated. It always chooses the simplest path to its fulfillment. Yes, possibly we have, because in physics you have that the path of least action, which is then the Lagrangian and all of that. So the Hamiltonian. So it is obviously really important, and I think that is a key feature inside all of these gauge theories. We have the SU2, SU3. They're all based on the Lagrangian, so they all have this path of least action within them. The question is, how do we unify all of them together? And I'm saying that the simplest method to do it is to use the 120 cell and the 600 cell, and that's really it. And that is actually a pretty simple model at the end of the day. Just that part of it alone. And then, of course, bringing in SL2. I think you can use SL29 as the group to cover all of that. So you'd have like 2x2 matrices with 9 elements, or you could use SL25 for the 600 cell, which is 2x2 with 5 elements. So you'd have like -2, -1, 0, 1, and -2, which again are the degrees of freedoms for the gravitons. So that's interesting as well. So it's kind of just keeps looping back on itself in interesting associations and connections. So it'd be great to get other people involved who are very knowledgeable in those areas, who might be able to shed more light on the deeper connections there. But it seems like all the particles have some there's this fiveness to the universe and to gravity that is sort of encoded inside everything in terms of its mass as well. I don't know. Perhaps that's where the mass comes from, but all of this needs to be fleshed out further. Like when you take the dual of the 120 cell, is the interactions between the gravitons what generates the mass values? I don't know. I haven't gone there, but it's just a possibility. Okay, so updated DECM with, so this is the other model with the dodecahedron, which is interesting. I'm not entirely sure what was meant earlier by collapsing the dodecahedron into a two-dimensional thing. I assume that's a projection from 3D space to 2D space, which would probably be useful. He might have been relating that back to what Emmanuel was saying about the graviton needing to be two-dimensional in order to be massless. There's none of that really in the model I have, because each particle sits on a vertex, so they're all point particles in that sense. But they have their own, rotations, so that's what gives them the mass and all of that. Or, well, actually, that is part of their gauge theory, and I should say. Okay, so with superluminal graviton condensate, in the updated model, the superluminal graviton condensate plays a critical role in driving both the expansion and contraction. So I'd say superluminal graviton condensate, that sounds very kind of your area with or Emmanuel's work. And so I'd say that there's probably some sort of aim to unify the dodecahedron DECM model with Emmanuel's theories on superluminal graviton condensates. I'm guessing that's where that's going from. So that could be, but when you're talking about critical in the role of expansion and contraction, I'm not sure. Would that be the expansion of the universe, or I'm assuming that's the case. And as for the, well, we're not sure about contraction of the universe. That's not a. Oh, here we go. During the contraction, the evaporation of the graviton condensate accelerates, hastening the universe's collapse, and ultimately triggering a big flash, which could lead to a new cycle of expansion. So it was expansion and contraction of the universe. Yeah, this cyclic expansion and contraction idea has been around for a long time. I think it was somebody tried to rule it out, and then I don't know what was it to do with the fact I've forgotten how they thought that maybe this wasn't the big bounce model, that it wouldn't work possibly because of the topology of space, that it's flat, but maybe it's slightly curved or something. I'm not sure. I'd have to look into that again, but I don't think it's so. Even like Penrose with his cyclic universe, he doesn't talk about a contracting universe. It's just it expands, everything cools down, even the black holes evaporate, and then you just have nothing. And because there's nothing there, the universe forgets that it's an unstable. Nothing is unstable, as they say, because even in the Higgs potential and all of that, the Higgs mechanism. But it's almost like the universe forgets that nothing is there and it just restarts, and that's the cyclic universe. But yeah, Big Flash, that is well, Big Flash would be kind of like the Big Bang, but I think Emmanuel has his own version of the Big Flash, which is how the universe ends in his model. But it's like, yeah, you need a very large time frame for that. I've forgotten what it is. It's like 10 to the 350 years or something. It's a huge number anyway. But it's an interesting idea. I don't believe in personally. I don't think contraction could happen. Yes, that's a possibility. I don't think it will necessarily. Rotation of the universe is more likely, and this is people are very happy to talk about expansion and contraction, but The idea of a rotating universe?
I think locally it can happen, the local aspect of the universe. But globally, I think it will be just superluminal thing all
You
the
don't
time.
think
But
the universe can expand globally, or?
yeah, it's only local. I mean, it's already infinite. I would think it's infinite, so the expansion doesn't make any sense.
I see what you mean. Yeah. Well, yeah. Well, from my
Contraction.
perspective, I mean, I do believe that the universe expanded, of course, but it was like there was an expansion.
The observable universe. It could be observable universe.
No,
real universe.
I don't think so. Like it expanded, but then it stopped expanding at a certain point. It gets to a size that it stopped. But the universe is infinite. But because there's two parts to the universe. There's the hyperspheric universe, which is four-dimensional, and then there's the tangent space, which is three-dimensional. And so we're working out the exact size of the universe from a four-dimensional perspective, and we're pretty close. Shouldn't take too long. Okay, so now there's more of a debate between, and Fugazi has posted some of his own research to help clear up different ideas. So the dodecahedral expansion contraction model. Okay, framework, integration of the superluminal graviton condensate. Right. Okay, so that is interesting. So yeah, because sorry, graviton condensate. What did I say? Anyway, I'm kind of getting a bit spaced from the amount of talking I've been doing. So it's very interesting. I think we have entire episodes, or what would you say, live streams on the subject of the anamorphic universe model and the anamorphic universe model hypothesis, and also I think a lot of them are called what is it? Figuring out the dimensions of the universe or something like that. A lot of them have that kind of title, about the dimensions of the hyperspheric universe. And all of them have incorrect values in it so far. I'm getting much closer to the actual value of the hypersphere. And from that, I think there will be a lot more connections then to hopefully back to things like entropy, different values for exact values for the constants of nature and things like that. I think there could be larger practical implications as well, maybe. But ultimately, the universe is very big, so it's practically impossible to actually get anywhere. But it would clear up a lot of info. Well, for instance, again, it's just useful sort of knowledge about the universe and how it works. So, for example, the anamorphic universe model explains what the anomalous redshifts of quasars seen in Holt and Arp's work, and also as a consequence, it tells us that so essentially quasars are like black holes, so they're indented into the surface of the hypersphere, and they also go up towards the projective point. So then when the projective point shines down, creates a larger shadow, if you like, of the object, which makes it appear more redshifted than it actually is. But if that's the case, then it would appear that all of the black holes kind of point up towards the projective point at the top of the hypersphere. So that means that they likely don't join at any point. So the idea of a wormhole is, how do you say that, Raj? It is disproven or likely disproven, if you like.
Wormhole.
Ruled out. That's the word I'm looking for. Ruled out.
Yeah.
But I have actually watched. I recently watched an American PhD student, and he was talking about his findings on PhD research into black holes, and I think even he was saying, look, the chances of if you look at the physics involved and the forces and all the rest, the chances of like a wormhole emerging out of this is basically zero. His thinking was that it doesn't happen, but I think there's something interesting about wormholes, and there's something cool about them, and you know, maybe there's some sort of engineering that could happen that could alter that, but I think such a thing might also alter their appearance in space. So maybe they wouldn't be as heavily redshifted. Their redshift would start going down as a wormhole is formed. So we could detect when, maybe you could detect when a black hole is being used as a wormhole. But anyway, that'd be fun.
You know, it's see, there is a vacuum. It's all intrinsically dynamic. See, that's the difference. See, what you said about a cube is a static. There's a picture at any particular time you take, right? It looks like that. But the universe is intrinsically dynamic, which means that in the dynamic situation, you can have wormhole. But that wormhole, how does the wormhole come into picture? Is because of the black hole and the white hole. We think that is a equivalent, like Noether's theorem. You know, if you do symmetry, so there is a black hole, there should be a white hole, and these two are connected by the wormhole. That's the hypothesis. That's the hypothesis.
Of course, yeah, but I think yeah. So that apparently anyway, you know, that there's just different thinking on this subject.
Yeah.
And I think that the results from the AUM or the Elm model, they just say that it's kind of like a plant, you know, like these plants where the tendrils grow up all the time, like a pine cone, and that's just the way it is. They don't link up.
Yeah.
And that's just the end of the story. Okay, so there's a bit of a debate here. It was, well, not complete. I mean, obviously, I'm open to other people's opinions. I'm not ruling out wormholes entirely. I'm just saying naturally, the way the universe is, it just has a form. Now, if you wanted to engineer it, but you'd be talking about alien civilizations going in and geoengineering black holes. So we're talking about like extreme weird stuff here, not normal stuff like at all. So possibly you would need to possibly beings even outside of our, like outside of the tangent space, in the bulk space surrounding the hypersphere and inside it and all of that, which is very possible. I'm sure there's things in there.
So one of the things I'm coming is that quantum black hole or micro black hole is like eventually I did a calculation, and I think in the next paper I probably put it, is very similar to graviton. Possibly, I mean, it's very high. It has a very high level of gravity in them. So
I see where you're coming from there.
Yeah.
I don't know, Rajan. I really don't.
Yeah, I mean, it's still a developing thing, and I'm coming with
keep it going,
Emmanuel to figure out that.
Right. So there's a bit of a debate here going on about graviton condensate. Someone's saying space. Okay, so
not made.
So the original part was not the graviton evaporate. How can a graviton evaporate? Which is a good question. It's a nonsense statement. And then, Fugazi replies, I said graviton condensate. But so the basic gist here is that GeoIntuition says space is not made from graviton condensate. So condensate, so this kind of reminds me of, the reason why I bring this up is it reminds me a little bit of what yourself and Wenzong were talking about in previous. He was talking about a superfluid, that I guess space-time or gravity is caused, well, you know, gravity is caused by this superfluid space-time that's moving towards planets. So I think it's an interesting idea. We couldn't really relate that to a graviton condensate, could we? Because that would be more solid state.
I think it's a local thing. See, graviton is a local distortion.
Yes.
I think in the local distortion, you can have the gravity and the graviton.
Isn't gravity an infinite force?
I don't believe. See, there is a weak gravity and strong gravity. So the weak gravity, which is like the open
Why
string.
do we like, surely it's all just one force. Why are you separating the two? Not saying that
Because
they're two different forces, are you?
okay, what happens is that if the two things are apart, they don't have any mass. They become massless. When they come together, they become massive. So there is a massless graviton.
There would always be, like, no matter how far these two objects are. Let's say there's only two objects in the universe. No matter how far away they are, there's always some attraction between these two objects because gravity is has infinite range.
Weak gravity. That's weak gravity.
Oh yeah, but it's only weak because they're far away from each other.
Yeah.
Then the closer they get, but it's all gravity. There's no, like, I know you can say this gravity is weak and this gravity over here is strong in a black hole or something. But like, there's a continuum between that weakly felt gravity and the very intensely strong felt gravity.
See, that's the thing.
So to be like, you have a musical note, you press on your piano, you play D or whatever, like a high register, then you play a D or C in a low register. They sound very different, but you can take the sine wave and smoothly, like continuously, just transform that sine wave one into the other. So the high note into the low note, weak gravity. So you can do the same with the space time. You can continuously and smoothly distort it from the weak to the high. So I don't, there's no quantum jump in this scenario. There's just a smooth transition. So like, I understand we can say, like, generally speaking, this is weak over here and this is strong. But ultimately speaking, when we're talking fundamentally, there's no difference between the force because it's a smooth manifold.
Yeah.
Yeah.
Okay. The problem
is not made from graviton condensate. So it says, would you say that, like, a condensate is more like solid state matter, whereas the superfluid is a different thing? It's not solid state, is it?
Again, it's very similar to what you said about continuous thing. The condensate has both aspects. It's a superluminal condensate. It is a dilute condensate, whereas the other one is concentrated condensate. The solid is like is a concentrated condensate is what a solid is. So you can argue that way.
Okay, so you're not saying that the superfluid that's not a condensate.
It's a condensate. It's a dilute condensate.
Oh, okay, interesting.
Very dilute.
So I enjoyed that conversation that yourself and Wenzong had on the. I mean, I'm not entirely sure I agree with the tired light aspect. I don't think it's needed, obviously, but I agree with this kind of fluid. If space could be a kind of a fluid, that seems to fit in with a lot of my research. And I also like the idea of having gravity as a kind of a surface tension. It's a fun way of looking at it, because you could just say, well, gravity is a force that does some weird things to reality. Or we could say,
actually, a gradient. I believe it's just a gradient.
Or we could, exactly, like a gradient, like the electric force. It could be like a force. And that's cool. Or we could say, well, let's reinterpret it as warp space-time. And that might actually be the answer, as a lot of people say it is. And I would say
the localized.
That's perfectly fine. I wouldn't argue with that to any major degree or anything, but I think you could also, like, adapt that to say, oh, it's some sort of surface tension in a kind of a fluid, just as an analogy to it, or even as a real.
See, the problem is the electromagnetism global and gravity local. That's the whole thing. So we distinguish between light, which is electromagnetic.
Gravity is not local. Like, gravity is as we said already, it's infinite range, just like electromagnetism, which is one of the reasons why you might think that the two are related, because they have very, very similar equations, for electric charge and Newton's equations.
And the reason is that the bosons can interpenetrate. They can go into each other. So there is no extent. It can go infinite. whereas gravity is associated with the mass. So if it is gravity, there should be a mass.
Right.
You should be able to measure the mass.
Yeah.
So that is the whole thing. So the mass, you know, if it is massive, in that sense, it cannot be infinite, because infinite mass does not make any sense. So that's the whole idea here.
Infinite mass does not make any sense.
Yeah, you cannot have infinite mass.
Well, yeah, but I mean, at this, yeah, I mean,
energy you can have. You can have infinite energy, probably. But even that,
they talk about infinite density, don't they, as well, at the center of the black hole?
Well, I think entropy or noise could be infinite, but I don't think signal can be infinite. You know, so signal is associated with energy and mass, whereas the noise is the non-conserved aspect, which can be infinite. I think the infinitely they're noisy. Like
interesting, but I don't know. Yeah, I mean, there must be some. I mean, there's obviously a lot.
So that's where the conservation of energy comes into picture, because energy by itself is a signal, which is a quantum thing. But the noise can be infinite. But the energy itself is quantized. So because of that, it is not infinite, but it's conserved in that sense. So that's, I think that would.
Another point here, in the case of Earth's near solid surface, how can you demonstrate its existence? So how does it act in case of free fall? So I guess, how would the graviton condensate act when you're dealing with free fall near the Earth's surface? I don't know. It's an interesting question. Maybe I suppose when Wenzhong is talking about, he's talking about, you know, the superfluid, that it's kind of flowing into the Earth or something. I don't know if I'd agree with that. I think it's more of a, you know, if I was using the analogy of a fluid, I would say surface tension. So it's again just like a static curvature within space. There could be like rotations and different eddies going on, maybe.
Talk about condensate.
Inner asteroid belts. I think gravity does work in the inner asteroid belt, doesn't it? I mean, like, the asteroids are moving around, you know, so. But
it's light.
The light. Rajan, maybe the question is, why didn't it work to form the planet that was obviously meant to be formed? Well, there is a theory that there was a planet there and, like, it was destroyed. But that's a cool idea, isn't it? Actually, there's a guy who came up with that called Tsarian, and he said that his idea was that the Earth, obviously this is moving away from physics a little bit into other areas, mythology and speculation and stuff, but that the Earth used to be like a desert planet, you know, like Arrakis or something from, you know, the movie Dune. And basically, so this other planet was completely obliterated by whatever force, doesn't really matter for the purpose of this. And then all of the, like, it was a water world, and so all of the water went into space as ice, and then periodically just rained down onto the Earth, quite rapidly, and completely altered the surface of the planet and formed all the oceans. And not only that, but there was, I think his concept was that there was it was a kind of panspermia idea. So there was life living on the oceans of this other planet called Tiamat, and it actually was like, even though the planet was destroyed, there was some of it was able to sort of freeze in space and travel over and then defrost, and, you know, because you can do that with fish. I think you can. There's certain animals you can freeze and then defrost, even those tardigrades and stuff. But so it's a fascinating idea, and it's really cool. And actually, related to another idea of this, you know, the concept of fish raining from the sky, like where are fish coming from? And his idea is like, they're actually up in space, like frozen in blocks of ice, and they thaw as they come through the atmosphere, and then just rain down on the. It's very funny. It's great
like concept. chickens falling from the sky type of thing.
Well, yeah, because
chickens, you know,
chickens can't fly, but there's videos of fish flopping around, falling from the sky, and I think the latest thing that happened was in Iran. But I think so another explanation for that, all of that weirdness, is water spouts sucking up shoals of fish into the sky and then depositing them elsewhere. But who knows? I really don't know.
In the cloud, when the sea, the cloud rises, right? I mean, the evaporation takes the water and becomes the cloud from the sea, evaporation of the sea. And then the cloud goes up there and then it condenses back and become rain. So I think you are imagining, the fish going along with that evaporation and then coming back.
No, I was talking about like let's say.
I mean, people, I don't know whether they're imagining like that.
No, I don't think they are. What they're saying is like as a giant tornado comes along over the ocean and sucks up the water. That's called a water spout. And then brings that across and then somehow so basically throws all the fish up into the sky and then they get stuck up there somehow. And then they drift across and then they fall onto wherever they're destined to fall on, like in a car park or something. You see this. There's plenty of videos of this phenomenon. Because when I was growing up, you'd hear about this. Oh, it rained fish in the 1800s, and everyone would be like, "Did it? Or is that just made up?" But now we actually we have video footage of it happening, and so it's a definite thing. I guess on a long enough timeline, all of the kind of concepts that we hear of will just be proven true, Bigfoot and well, what's going on with the UFOs in your country at the moment? There's a huge amount of strange aerial phenomenon linked with.
Actually, Emery is quite interested in that. He wants us eventually after he finishes the paper, we'll be working on that, like UAP things like that.
Well, is he going to come back on the channel to discuss it, or is
probably later? We finished one paper. I think it will be posted soon. Then there's a paper.
I look forward to that because he's talking about joining some sort of UFO group. Is it?
Yeah. So he already sent me something.
That would be great. Well, actually, Rajan, on that point, at some point in the future, I'm thinking of doing some research into UFOs here on this channel. It'll be pretty interesting. So we'll probably do it like in a live coding kind of scenario, but don't have to. But
you are coded about UFO?
Yeah, we're gonna do like a big thing on UFOs at some point.
Okay. So I think Emery will join eventually because he's interested in that.
Yeah, that'd be great.
In that
It'd be great to have Emery's input on it, and but it's part of a much larger.
He has done lot on tardigrades. Tardigrades, he has done quite a lot, I think.
Tardigrades.
Yeah.
Do you mean those little sea? What are they called? Water bears. The little tardigrades.
I don't know. It's connected to you, but UAP. There was a congressional hearing. You know that about the UAPs and things like that. So there are both sides. The one side is saying that definitely is there because they see the pilots, the military, Air Force people. They see this one. They said there is nothing that explain that the faster because they move around too fast. There is nothing on Earth that can explain it. But there are other people who said that certain type of flares, things like that, may look like that, things like that. So that debate is still going on.
There's possibilities. I mean, there's definitely technologies that could explain, for example, what we saw with the Tic Tac phenomenon. So there's potential there. There's different sort of effects and technologies out there that can produce those sorts of effects. Now, so Fugazi News said, "Have a nice evening, folks." So I guess he's taking off.
Signing off, bro.
And Geo Intuition says, "Your model is very good. You have to connect it to crystallography." Yes, I completely agree with that. There's a lot. We were discussing a lot about the crystal symmetries. Oh, Fugazi's still here.
Oh, Fugazi's still there. Okay.
Yes. So we do have to connect it through. Well, I suppose we kind of are connecting it a little bit through the Oh, he said he was talking to Emmanuel. But so we do. So you know this idea we had where there was like a 5-fold crystal symmetry and a 4-fold crystal symmetry. Right, and there was an idea about. You were saying that the 5-fold would be hidden inside 4-fold, wasn't that?
Yeah, I said that the macroscopically 5-fold cannot.
Oh, that was it. Oh, yes. So macroscopically, but as you get down to the quantum level,
yeah, you can.
It begins to show itself. Yes, the fifth. What would you call it? Fifth axis, if you like, or the fifth. Rotation, and then. Yeah. So it's kind of it's hidden on the macro scale, but as you get further down, it emerges, it becomes more obvious. Yes. We were discussing, well, how would we go about visualizing this or describing this mathematically? And well, I think today during the presentation, you saw how the dodecahedron, yes, which has pentagonal faces, transforms into the pyrohedral cube. So it goes from a 5 to a 4. I think that could, that's why I was bringing up the whole 5-fold crystallography and the relationship to gravity. But I think there's something very abstract about this. I mean, obviously you can see, like, there are 5-fold crystal groups, isn't there, in terms of quasi crystals, and it does pop up in certain places. You know, you can have dodecahedral crystals as well, which obviously have 5 pentagonal faces. So yeah, so the quasi crystal then is an interesting one, because if we couldn't project through that, you can create, or is it, if you couldn't project through a 600 cell, you can generate quasi crystal patterns like that Penrose uses. And
the tiling, you mean? Is it like
the tiling, exactly. Yeah. So there's, oh yeah, and we did some work. We did some work on that with leptogenesis as well. So I don't know. It's pretty interesting. There's a lot of spin-offs. You know, you could the quantum gravity research people, Clee Irwin, and then the string theory people. You know, it could all connect, especially, and also your intuition about what was it you were going on about a lot with the prime factorization? That seems.
Oh yeah.
Yeah, and do you remember we did?
Yeah, I mean, I looked at your thing, like 16 is 2 to the power 4, things like that. And that what it means that, you know, how the massless and the massive is connected by the prime factorization, I think. In the end.
Yeah, I think it's weird.
The degree of freedom also. Degree of freedom.
Yes.
When you do prime factorization, it changes the degree of freedom.
Yeah. Well, we're going to look into that again more in future, and it's going to relate back a lot to, well, more into the string theory side of things, and but only just briefly kind of touching on it. And I don't think, you know, if someone with a bigger string theory kind of background.
You ought to also give a discussion about Bianchi identities, because that seems to factor into this degree
that
of
would be
freedom.
Great if you could look into that, because I know you've done work on, like, you mentioned the Ricci tensor. I've been sort of working on my own, you know, separately on the numerical relativity methodology that I'm coming up with that can be used on computers. But I'm finding that the more I study, you know, the field equations for gravity, I'm noticing a kind of a disconnect between my methods and the field equations, particularly to do with the Ricci tensor and certain other aspects. And so I think, yeah, because so I don't think I think my model is like effective. It'll work, but I don't think it's exact. So it'd be great if you could sort of dig deeper into these concepts of the Bianchi identities and maybe come back with some enlightening information for the rest of us, so that we can more properly understand what's going on with especially the degrees of freedom and the irreducible representations of the symmetric tensors of degree 16.
I think I will automatically go, because the next one, I did a reference frame. I have sent that paper and it is kind of revised, but they are reviewing again. So
Right.
if these 3 papers, already one is there. You already saw the type cut. The next one is coming up, the Cayley proof. The third one is in the review, almost the review level. And then I have the particle, the particle aspect, which is the real thing, which is where your space will start coming into picture. And at that time, I'm sure I will start looking into these kinds of things, degree of Bianchi and all those things.
Oh,
so
great.
It will be like, right, probably by January, I hope that we'll get to that.
Okay. And so what are you doing? You're not going to be around next week, is what you said.
Yeah, next week we'll be there, 14th. But
you are?
20th, okay. The following week, the 20th, we are going to New York. So I think we can take it off, because everybody will be on vacation. I think probably you also, maybe with your family, Christmas.
Yeah, over the Christmas week. Yeah.
Yeah. So after the 14th, then then I won't come back till the 4th of January. So after the 14th, it could be the 11th, of January that we start our thing. So there'll be almost a month gap of not having the text. Almost a month, slightly less.
Right. Okay.
Yeah.
Well, if you ever want to get on and just do an impromptu,
you can do a Christmas special. If you want a Christmas special next week, you can do.
Oh yeah, it's an idea. Christmas, but if you ever just want to get on and just do like whatever, you can just.
Yeah. Yeah, you can put that on.
You just do your own uploads of, like, if you have ideas or whatever.
Yeah.
Physics. Okay, so from an astrophysics position, crystallography deals with hydrogen and helium, which is the high percent of the known matter.
The known matter.
This is correct, yeah, because then what I've forgotten the ratios. It's something like 74 to 25 or something, and then 1%.
The stars, the star. Yeah. The material of the star is a hydrogen and helium, yeah.
And so this is like a big, what would you say, success, of the standard model of cosmology, where it predicts these exact ratios based on a hot Big Bang or something, like a Big Bang model where, I've forgotten exactly. It says it's dense and expanding universe, that kind of Big Bang model. So I don't know. I mean, it's an interesting one to explain a bit more. See if I guess it's a prediction they made, and they're happy with it. So I wonder how much crystallography plays a role in that. I think there's possibly crystallographic sort of elements within maybe the orbits of the known elements. That seems like a reasonable.
I think crystallography may be closely connected with the frequency. You mentioned about a frequency, amplitude, and things like that.
Yeah,
you may have a direct connection with that. You may have some connection with that. So that's why it's so pervasive in that sense.
Yeah. So we live on the lithosphere. That's true. The lithosphere. This person obviously has a good geo-intuition.
Good knowledge of
good knowledge of geography or geophysics.
Geology, geophysics.
Yeah. Okay, so use the model to explain hydrogen element. All right, that'd be amazing. That'd be awesome. Perhaps we can work together on something like that.
Yeah,
I find I need to how do you say, get more familiar with is it the Bohr model of the atom? Would that be the? What's the? No, it was Bohr, I guess.
Sommerfeld, different people.
Yeah, there was a lot of people, I suppose. So yeah, all of the you use those different numbers. I've looked into it before. Yeah, it'd be good. And then of course to go from hydrogen to helium, and
helium paper.
Yeah, see the helium. So that's where it gets more complicated. Obviously, they've never been able to do like what do you call that? Use the same thing for the Earth's geomagnetic field, spherical harmonics, that kind of thing that they use for the electron shells, orbitals. So yeah, it's definitely, actually, that is something that I didn't include in the presentation. If you look at there's these things called Hopf vibrations for the 120 cell. And they're kind of discrete Hopf vibrations. So actually, it'd be good if I could just, rather than describe it, just show it, because I'd be here, So if I go to 120 cell on Wikipedia, and I'll just share my screen once I find it. Click off that. I think it's somewhere. It is 120 cell, isn't it? Yeah. Okay, so yeah, I'll share that. Where's the? Yeah, back here. Okay. Share screen. Entire window. Share. Okay, you can see that, can't you?
Yeah.
Oh, it's gone. Oh, it's back. Okay, great. So this is kind of interesting because so we have these rings in the 120 cell, and you can see how they intertwine with each other. It'd be cool if they were intertwined in a way that was related to the kind of gauge groups. Like this would be the electric part of the force, and this would be the magnetic part, or this would be the electromagnetic force, and this could be like, like SU2 or something, but it doesn't actually work like that. It's just a bit too simple the way they're interlocked. It's very I don't think there's any real use in this. But this one is kind of interesting because if we compare it to some of the spherical harmonic, I think I'm saying that right. I hope I am. The spherical harmonic, how do you say? All of this stuff with Gauss's coefficients and all of that. So you can wind up generating these exact patterns, which also appear in the orbitals of, I think, the hydrogen cell. So this would be one orbital, and then you have these kind of these balloon sort of shapes that come out of the top and the bottom of just the different hydrogen cells when using spherical harmonics. And then so it's interesting that these forms are kind of embedded inside the 120 cell. So it might be fun to apply spherical harmonics to the 120 cell in general and see what emerges out of that. Would you get, like, for example, if there's 120 cells, how many elements are in the periodic table again?
Oh, now they increased 100 something. More than 100. It used to be 90s, but now it's more than 100.
Yeah. So it would be interesting if there's a possibility. I don't know. Well, let's just look up the periodic table quickly.
So right now, the Einsteinium, this and that, hafnium.
Okay, so it's gone up to 102.
Yeah.
So, question, because I've developed my own periodic table that yeah, I could show that actually. You just have to look for it first. periodic table. I think actually I sent it to someone on ResearchGate. So if I look, oh no, that might not be the way to look for it. You've seen it though, haven't you? It's a circular periodic table.
Oh, I might have. Oh, based on your 120 cell or 600 cell?
No, it's not. But that's what I'm kind of thinking. It would be interesting if we could.
How did you develop that periodic table? I don't
know. I think I developed it based on cubes, like nested cubes.
Oh.
It's a good question. It's been so long since I looked it up that I've been looking at it that I'm not entirely sure where I have it. Maybe I'll just search periodic table 2. Yeah, that's it. Okay. That's good news.
Did you program it? How did you get that? Did you program the whole thing?
Hang on a sec.
Did you code it or something?
No, no. This was. I'll show you now exactly what it is. I think I used like a Photoshop. You know, kind of Photoshop editing.
Oh, Photoshop.
So can you see that? Yeah.
Oh, I've not seen this actually. I don't know.
Okay, so you can see the model is there's hydrogen there and helium, and basically this all the black dots are electrons in for the highest element, which is what on this one, isn't it? Oh no, that's 118. Is it? 116, 17, 18.
That's what I said. Yeah, so I just gone up to that. I know that.
Or something like that, or ununoctium.
Ununoctium or something.
Oh no, I think it's ununoctium.
Ununoctium. Okay.
Yeah, and it says it's unknown. Its mass is unknown. Okay, so this one goes up to 118, whereas the one on Wikipedia only goes up to 102. So I don't know why there's a difference there. But you can see
these are all artificial. These are all synthesized. I think they are not natural.
Yeah. The further ones out and they are synthesized, and they're also more unstable as well. So they only last a little bit. But there was supposed to be some sort of modular kind of concept behind this periodic table. So but it's been so long that I haven't looked at this in a while, but there was supposed to be some relationship that builds up between some of the elements as you move out in like a modular kind of pattern or something like that. Mm. So I think, but I'd have to go back and look at that. But I think visually it looks quite good. So
quite symmetric and quite harmonic in a sense.
Yes, it reminds me a bit of the
the orbits, the sun, astrophysical.
Oh yeah, well I was thinking more of the Mayan. What's it called? The sun calendar or something?
Oh, Mayan calendar.
Yeah, there's some sun.
Oh yeah.
Yeah. Calendar. The Mayan calendar with anyway, it doesn't really matter.
Mayan calendar.
Based on the. Okay, so all right, so we'll look at I'll take a look at that helium paper later, and I might have already looked at it based on the standard model. Yeah, I find the standard model I don't find it easy. Yeah.
I have a lot of questions on them.
Yeah, it's pretty rough.
It's still a questionable thing. I mean, it has been proven it is probably experimentally more accurate, but there are a lot of things that it questions. I mean, only the weak theory I think is explains really well.
What is this?
The standard.
Oh, yeah, I think you're right. Yeah.
the weak theory is fantastic. I mean,
Yes.
it is almost 100%, close to 100%. But
Yeah.
but I don't think either strong theory and my feeling and gravity definitely not the standard model.
Well, then
Because
the
even-
Higgs would be kind of be there as well, wouldn't it? With the weak.
Yeah, Higgs.
Very, very
Higgs is part.
connected.
He
Very
connected with the weak theory,
Yeah.
and then Higgs developed from there, connected that to the.
Well, hopefully
boson.
now, like this 120 cell model, like because obviously the work, you know,
That's fantastic. What you have done is, like Emmanuel said, you extended that like a dial. You increase the dialing ability of that. You are
Yeah.
dialing from a.
Notice I use like very minimum mathematics to do that because that's what's kind of needed.
Oh,
You
what
could
is
imagine,
quartic
like-
equation? Quartic equation. What is that? I mean.
Oh, the quintic equation.
Yeah, quintic.
Yeah, that's a good question. You know when you're trying to find the roots of a quadratic equation, and you use that. What's the
minus b plus or minus square root of b square minus 4ac by 2a.
Yeah, that's
quadratic equation. Quadratic equation.
Brilliant. Yes, the quadratic equation, and then I think you can create a cubic equation, and actually the cubic equation was discovered first or something like that. I think, or actually, and the person who discovered it found, you know, that's where they discovered imaginary numbers, which obviously play a big role in the quadratic equation, like you said. And then so you can go on. I think is there the quartic, but then was it Galois theorem or the whole is it number theory or group theory? He was able to use group theory to prove that there's no you can't resolve for the quintic equation or something like that. There's no solution. Like there's no actual equation for like you have with the quadratic equation. You can't create a quintic equation
for the cubic thing. Is it a cubic root? Is a cubic root? No. Is it a quadratic equation x square plus
the quintic now is 5, right? And cubic
quintic x to the power 5. X to the power 5.
Yeah, quintic would be 5. So that's why it's kind of related to everything I'm talking about with the 5-ness of gravity. So maybe like because there's maybe at the root of the universe is this 5-ness, you know? See?
Your fingers,
yeah.
and the symmetry, chiral symmetry you have.
It's getting spooky. So maybe the higher energies where everything is, what's the word for that again? Where it's not unbroken, so that you have this 5-ness, but then the 5-ness is kind of non-solvable. It's somehow anti-symmetric, and it just needs to solve itself. So it kind of breaks, and it breaks into the 4 fundamental forces then through this dual representation, which is the 600.
5 is also a prime number, so you cannot factorize anymore. You know.
Oh, right. It's an irreducible representation itself. So if you want to get down deeper, you got to break it apart and do something funky with it. Maybe that's what's going on. So like I say, I come at things from a very non-mathematical kind of way. I like visual explanations.
Yeah, fantastic. Your thing is beautiful. Yeah.
Thank you. And I like to code. I like to code things so that they become visual and explainable. And like easily understandable. I think a 5-year-old could understand the basic concepts that I put forward.
Yeah, the one that is coming up.
Yeah.
For me, the Gaili proof, I do include a code, Python code, to generate the signal. So I compare the signal I generate from the abstract, and then I code it because they have some methods I found in the literature. So I use that, and then I see the comparison between what I have found with that. So I think you will understand a lot more. I'll work with you because you are more expert on the coding aspect. And you can use that code. You can include that code in your code, and you can combine that to space time.
That's great. That's what coding's all about. Share your code. Yeah.
Once it comes out, it may come out in a couple of weeks. So by the time we come back from the break, from the Christmas long break, I think we'll start working together. By that time, I hope to finish the last paper on the particle. That will be my part, the time part. But then everything else will be your part, which is the space part, which will become important for particles.
Right.
As soon as I get,
I've now got like time and space are like part of the quantization at the root of the whole system, like
discrete.
But I mean, it is interesting because I think for a while now, I suppose relating to the 24 cell and the fact that we have like, is it, it's the same in bosonic string theories based on the 24 cell as well. And so you have that kind of 6 times 4 thing going on. And that's really at the root of bosonic string theory, where you get the 24 dimensions. But what is that? It's like, so I think you're saying it's 6 dimensions of space times 4 dimensions of time or something?
Yeah, 4. You already have the hyperdimension, the 4 hyperdimensions. You already, you presented the anamorphic universe, right? It's part of the anamorphic universe model.
Yes, that has 4 dimensions. Yeah, 4 spatial dimensions. Yeah.
So that makes sense. So, and then the 6, the tensor, which is the 6-dimensional, kind of a 6-dimensional time.
There is a 6-dimensional element that we haven't yet gotten into in the 120 cell, and it's to do, it all links back to the prime factorization stuff. Remember, we did a lot of work on prime factorization where I was trying to build these fundamental domains, like, what do they call them? They're called lattices, I think, in bosonic string theory, where if you go out one side, you come in the other. So it's a torus.
Oh, you can come out. Oh,
yeah. And if you just keep adding dimensions to them, you can create higher and higher order dimensional tori. So the idea is then we can take the 120 cell polytope, the fundamental domain of the hyperbolic tiled space. We take the 120 cell fundamental domain, and then we wrap it around so it connects top to bottom. Then we wrap it again so it connects side to side. And then we don't need to do what, I've been having this debate with Christian for the last number of years.
I-space thing.
Yeah, because he's saying that in order to glue the inside of the torus with the outside, anyway, we don't need to go there because you could just, in order to create, let's say I have, like, how do you start with say I have a piece of paper and I glue, or you have a tube, we've glued two of the edges together, and then we glue the ends. Then now we have a torus. But if I just rotate that again and back and glue it back, that will be that's kind of like a 4-dimensional torus. Then that is the definition of a 4-dimensional torus, how it's constructed mathematically. And I think he's going further. He was talking about a 6-dimensional torus, and that's fine. But we don't actually, because we're dealing with a 4-dimensional polytope that we then bend in that exact way that I just explained. And that means that we go from 4 and we have to add an extra 3 dimensions, because the first one and the second dimension bending all happen in the same dimension.
XYZ, like the XYZ split.
Yeah, exactly.
Like you have 1 dimension, and then you have the one that's coming this way, and then coming this way, another one.
Right.
Like 3.
So then when you add all those together, you got 4 plus 3. I think that's 7. And then if you look at the, what are those things called again? The exponentials of the values for the prime factorization results of the irreducible representations or other dimensional irreducibles.
I don't know, but it's connected with the BIG
also these
Euler form.
Sorry, just one last point, Rajan, because you'd be interested in this probably. The symmetric group order 6, which had like 720 elements, which so then you have the the prime factorizations were what? 3 to the power of, no, sorry, 2 to the power of 4, 3 to the power of 2, and 5 to the power of
3 square times 3 to the power 2, right?
Yeah, and 5 to the power of 1, right?
Yeah, yeah.
So then if you add those together, that's, well, just ignore
720. Multiply. So you get 720.
No, I think if you
add them. Add them. Okay.
Yeah, because if you multiply the numbers, you get 2 times 3 is 6, but then you have to add the other guys together, and that'll be 7. So there's this. It kind of goes back to this idea of some sort of 7-dimensional thing, but there's also 6 dimensions involved as well because of the torus. Oh no! Wait a second. Hang on. We said there's. See, there could be. I'd have to look back into it, but it looks like there's it either winds up being 6-dimensional or 7-dimensional, and that's a kind of an interesting ambiguity there. But ultimately,
and also
the thing is just it's just a sort of a mathematical sort of abstraction for the generation of an infinitely tiled hyperbolic space. But we could also say, no, that's actually a real thing, and that the entire universe is like sort of you can compress it, like in a sense, contain all the information just in this 7-dimensional torus or 6-dimensional torus, whatever it is, and that's fine, you know. So you can pick the universe up and like move it to some other location if you wanted, but the interesting thing about that is that it then ties deeply into string theory because string theory is all about these lattices and strings wrapped around toruses and stuff like that. So then we get into all the craziness of who's that guy with the modular forms from India, Ramanujan, was it? And all of this
the
math there that connects all the way back to the standard model and all of the work that other people are doing on neutrinos and connecting it to modular forms and stuff. So it could be that's like very technical maths kind of stuff. So, but I think it's plausible that that is the connection that the string theorists were looking for. So the actual group that was and again, you know, the Calabi-Yau structures are meant to be 6-dimensional. So it makes sense that this torus would be 6-dimensional on one level. And then, yeah, so because like I was listening to one physicist saying that, you know, he had no doubt in his mind that no matter what the solution to the universe is, or to this problem of quantum gravity and the theory of everything is, the theory that the string theory would appear in some form, like it would be connected, might not be the whole thing, but it would have some mathematical connection deeply there. I think that's probably where the connection is. And then obviously Christian's ice space.
Yeah,
that's got to appear as well. That's too weird not to be real. So maybe there's
in terms of constants, I think he probably has a point. You know, Christian, in describing the constants, the connection between the constants.
Yeah,
he's on the right track on that one. But in terms of the logic, the actual structures, it could be different. Your thing is much closer to what it should be. Geometric structure is much closer to what
he keeps finding this number 6 in terms of exponential. You know, so
certain numbers.
So he was looking at the idea of 6 dimensions, and I think I agree. I think his geometry was a bit off. So, but everything else looks good.
But his numbers seem to be perfect. His numbers are
very, very accurate. And then, of course, the issue there with the fact that he uses phi, like the golden ratio and the golden mean comes up a lot. And then if you look at the 120 cell, the golden ratio is all over the place in that, you know? Mm-hmm. So I think it would be good if Christian sat down and had a look at my work and said, well, can I use these 4 vectors, or can I use some of these values and see if I can, maybe prove
Yeah,
them
he
all.
can check that.
He tends to use his thing to kind of prove other people's models, and I think that's interesting.
Yeah.
But he'll also have to. He could also try and not prove his model, because I think it kind of proves itself, but maybe prove other things that he's not
apply his model.
Yeah. Anyway, it'd be fun to try, but maybe it's not that interesting because it's only about 6 values or something that appear in the coordinates. But then you can scale those to any different size. So he has like an infinite number of values to play with. Not really an infinite number, but because you're only going to use a few of them. But there could be a few that are good, and then he could maybe try and scale the 120 cell based on the constants of nature. That could be an interesting one. Because there's a lot of different ways that it could be, we could take the research in future.
I can show a brief thing. I mean, I will appear in my next one, but an interesting thing I find, I'm not going to detail, but interesting thing I find is, this is the calculation I did. It's a very simple calculation based on Newtonian thing and all that. But we can pull up that.
Oh, do you want to add that to the thing?
Yeah. So, I don't know if you can see that.
Yes.
So, it's a very complex. I mean, I had to rewrite some of it, but I equate that. It's a very simple equations of gravity and everything. But finally, I come up with these constants here. You can see that. Constants right there. That is power and energy. So it is it's the Stefan Boltzmann sigma. So let me rewrite that.
Oh, yeah, okay. Very good.
I know, yeah. And then then a few things. And then Boltzmann constant and universal gravitation divided by Planck divided by the speed of light. And that connects between the gravity of the micro black hole and the temperature, temperature, 0 point and micro black hole. So 0 point, So I think it's a very fundamental thing. The paper, I think the next paper or the following paper, I will have that. And I think what I'm trying to see is that the connection between the micro black hole and the graviton. I think it will come out. So, but it's a very high value. For the micro black hole, the gravity equivalent is like 10 to the power 22 of that of the Earth, and the value comes exact, and that's a surprising thing. It's 9 point. When I calculate, it's 9.7 times 10 to the power 22, and 9.8 is the Earth's gravity, right? Meter per second. Actually. Yeah, so it's almost like the power 10 to 10, and 10 to the power 22 also makes sense to me because it came up somewhere else. So it seems to have some kind of a connection that they were talking about the graviton condensate, things like that, right? For the Earth and connecting with the Earth's thing. So somewhere they were asking what is the connection to the Earth, things like that. I think that maybe it may factor into that in the point macro, the small thing, and that has the because everything is condensed to that mass. It has that 10 to the power 22 gravity with the strongest gravity probably possible, and then that when it connects, it expands the weak gravity thing, which is what we see on Earth
as a gradient, like you're saying. So that's really, well, that sounds really interesting, Rajan. And at some point in the new year, it'd be great if you could, even just do like a short 3-minute presentation on your best idea.
Yeah, and also by that time, I hope that it will come in the paper, so I can pull up the paper.
What you're talking about there sounds very good, but it's still I think it would be good, you know, if you just do like a load of short ones first.
Yeah.
So we see like which is the best, and then we can run with those.
Highlighting.
So yeah, but we're gonna leave it there, Rajan, because I need to get some food.
Sounds good.
Anyway, brilliant.
We'll see you next week. Yeah, next week we'll see you.
Okay.
And then yeah, you can switch off that because to discuss the other
yes,
one.
Good idea. End the live stream there. Okay.
Yeah.
Thanks for everyone for joining in. That was great. I think that was the most people we've ever had. So that must be down to Emmanuel's
fantastic discussion with Emmanuel and all that, you know, and then we had a nice straw with the geo-induction and Fugazi news.
Oh, absolutely.
Nice debate. I mean, question and answer. We want to see that more often. I mean, further presentations.
See people engaging and disagreeing even. Why not? Okay.
Yeah, it's a debate. Yeah. Thanks.
Okay.
Okay.